This conference will now be recorded.
Hello, can I know, am I audible to everyone?
Yes, you are.
Yeah, thank you. So, well, since I hope everyone is here and we have a lot to cover, we really should begin today's webinar. I really appreciate you all for attending today's webinar. A very good morning, afternoon, or evening to one and all present here virtually with me today. Let me introduce myself. My name is Jessica Rees, Conference Secretariat at Coalesce Research Group LLC, and I will be available for any of your queries or questions throughout the webinar to help you out technically and organize the webinar successfully. For the next 5 minutes, please allow me to give a brief description about our organization, Coalesce Research Group, and also the further instructions. Coalesce Research Group LLC is very delighted to welcome you all the speakers, supporting associations, students, and delegates present virtually with us today, with the aim mark the scientific excellence by facilitation conversations, sharing knowledge. Coalesce Research Group follows through the objective of setting standards in delivering excellence in the research among the researchers, academicians, and industries, promulgating the research through conducting events and online webinars from various fields of science, especially from the stream of medicine, science, engineering, and technology. Within a short duration, we have succeeded in creating a platform for developing a strong professional network with the people across the world from their respective fields that they haven't connected in a while. As a global scientific event organizer, we plan and carry out international conferences, meetings, seminars, symposium, and workshops, providing the best delegate experience, excellent networking opportunities, conversations leading to innovations, learning new opportunities, lasting working relationships, and professionalization within the professionals around the global network. Just recently, we have also started our own platform for open access peer-reviewed scholarly literature, where all the content is freely available without any charge to the reader. We aim to share the news recent advances through scientific publications, which will help in minimizing the border and contributing the use of research works of eminent authors, scientists, researchers, research scholars, students, etc., across a broad spectrum of medical, clinical, pharma, and engineering scientific disciplines and its subspecialties to promote the ideas which will guide the development and facilitate the use of scientific information and ensure its quality, and also will be the connecting link between researchers and scientific community. We are committed in ensuring that our journals are disseminated worldwide so that the researchers are able to access our content whenever and wherever they need it. As being very new journals, we have coined up some interesting journals and have also found the editorial board, and will be very glad if any of your today's attendees, the speakers, students, or delegates could extend your support by checking the journals and will be interested in publishing the inaugural issue at any of our journals according to your area of expertise. We will also send an email with all the details about the journal after the commencement of the webinar. Do take your time to check the website. Finally, I would like to thank all the attendees and participants of today's webinar and hope you enjoy the webinar and gain knowledge from the sessions today. We also hope your participation will contribute to new research findings and that will lead to new collaborations and research initiatives. Before we start with the sessions, I guess some of you will be new to the GoToMeetings app. Let me just explain you the important tools required for your presentation. On the GoToMeetings app or web page, you can find four icons at the bottom of your screen. That is mic, camera, screen, and end. Mic is like click on that mute or unmute yourself. I request you all to stay muted while other speakers are presenting their research work so that it doesn't cause any disturbance to them. Camera, you can use this button to share or unshare your webcam. If you have the option to share the webcam, you can do it, or it is completely your choice. Screen, you can use this button to share your screen. This is the main part during your presentation. After I call your name from my side, I will be making you the presenter, and only I give the permission you will be able to share your screen. So once I make you the presenter, you can click on the screen button and you will find a pop-up window to share your screen. And this is your fourth icon where you can use this to leave the session. On the top center, you can use the options to change your display settings. At the top right corner, you will have three icons, that is people, chat and settings. In the chat option, you can chat with me or any other participants. For the settings, you can use this button to check for the settings of your speakers and microphone. So as mentioned, kindly remain muted during the presentation so that the presenters don't get disturbed. And for any questions, you can ask the questions or you can send your questions in the message box too. Well, let's not take much of your time. Finally, I would like to request you to please give your brief description about yourself before starting with the session so that we can know about you virtually. And now let us move on to our session, and the first presenter of the day one webinar is Dr. Svetlana von Gratvorsky from Institute of Radio Engineering and Electronics of RAS, Russia. Hello, Dr. Svetlana. Are you ready with your presentation?
Yes, I'm ready. I am
Okay,
happy
thank you.
to meet everybody.
Thank you. Thank you very much. I'm going to make you the presenter. You can share your screen and start your presentation. Yeah, it's done. Now you can share your screen.
Wait a moment.
You can click on the third button on the bottom of your screen, that is screen button.
Can you see?
No, it's not visible. Please click on the screen button. It will ask you for the permission. Yeah, it's visible now. Now you can start your presentation.
Okay. Moment, but sorry. I'm
Yes,
so
it's visible now.
it's visible.
Yeah.
Oh yes. Okay, very good. So my report is about bottom-up nano integration of semiconductor nanowire in highly sensitive bio-nanosensor using a shape memory alloy nanotool. Institute of Radio Engineering and Electronics is placed near Moscow Kremlin. This is here, if you see. Now, all of us are living inside coronavirus time. And because of this, we are not together in the same seminar room, but we are only online. That is why this is very important to sensitive bio-nanosensor for viruses and other infections. One of the best way prevent pandemic is control to the diseases by detection of viruses at trace level in air and in real time. These viruses also in public places, theater, shopping center, railway station, school, and other. But we don't have suitable technique for this. Just now, current diagnostic is mainly used is polymerase chain reaction. This is for detect of specific nucleic acid of viruses. This technique is costly and time consuming. You know, everybody knows that this is not in real time. And this cannot operate remotely sensing. Also, this technique needs skills personnel for handling samples and interpretation of the result. Therefore, in this is needed development of low cost and not quickly detection technique for different viruses, because can be also other viruses, not only coronaviruses. And in this report, we offer novel nanobiotechnological sensor based of nanowire PET transistor, field effect transistor, for real-time detection of single virus. Only one virus can be detected by this technique in air and human samples. So this is challenges just now, so such things don't exist. This will be done by nanotechnology, special mechanical bottom-up nanotechnology. What is nanotechnology? There is 4 different types of nanotechnologies. This is, for example, bulk nanostructures, solids, and there is also there is synthesis of different nanostructural solid using self-assembly. All this is bottom-up technology, not nanotechnology. There is also top-down nanotechnology. This is nanolithography, what is used in everybody's smartphone and computers. Also, this is microscopy. This first bottom-up nanotechnology, how this meets self-assembly and large nanostructural solids. For example, bulk solids go inside fragments, and after this it takes place nanostructure like clusters, or other way from other side, this is top down, other way from atoms we get a cluster and also nanostructural some condensed matter. Top-down lithography, in the meantime, used for nearly for everything. This is for smartphone, computers, and so on. This is a very, very expensive technology. This is facility cost many million or 10 millions of euro. And we offer bottom-up technology. This is not so expensive, and this can be also hybrid with bottom-up, top-down with bottom-up. With what we mean by this bottom-up nanotechnology? Everybody knows that there is many individual nano objects. For example, nanowires. This is indiphosphor nanowires. This is also zinc ore nanowires. And from these nanowires, we try to make special nano devices, also nanosensor for individual viruses. Why nanosensor from individual nano object can catch a single virus? Because they are the same order like viruses. Viruses are some nanometer or 10 nanometer and or 100 nanometer, and the same enlargement has nanovirus and some other nano object. What shall we do for this? For this, first of all, we must make nano manipulation of these viruses. Usually inside everyday life, if we need something, we take this with our finger, and we see this with eyes. And in nanotechnology, we must also see something and also cut this by something. And by this way, we offer nano manipulation using shape memory alloy nano tweezers. And after this nano fabrication. What is, for example, possible? This is gold. This is one of the example. This is a nano computer from with nanoprocessor or nano memory, nano antenna, nano sensor, all is done from some nano wires. This is one of example of some concrete device. This is ND phosphor nanowire wire that is building block for nanoscale bottom-up nano assembly. This is per nanowire, ND phosphor nanowire. This is N nanophosphor nanowire, and this cross section is PN junction. But from this, this is electrode. From this PN junction, it is possible to make the smallest in the world nanotransistor, the smallest in the world LVD, and many other devices. So this cross junction is a really building block for nanoscale bottom, nanoscale electronic, optoelectronic, and sensoric. What is about, there is also other possibility for make a bio-nanosensor that is also not possible to make using top-down nanolithography. This is based on carbon nanotubes, FET transistor. FET transistor, this is spelled a FET transistor. This is a very important technique because this is possible to catch, to detect very, very small amount of viruses, for example, wine virus. But this is not planar technology. You see, this carbon nanotubes, this must be bent, and this is not planar. After this, this electrode must be bent. After this, this is placed carbon nanowire. Over this carbon nanowire, it will be placed a special antibody, this is shown. And this is also together with PDMS microfluidic channel, all this on the wafer. And when during this nano or the microfluidic channel, place something, for example, air, or for example, some from nose, or mouth, from nose, or some other analyte with virus or not. When this analyte, this is very, very small amount, when this is go through this microfluidic channel, and this nanowire or carbon nanotubes with is functionalized with especially antibody. After this, this virus glue to this nanowire. And what takes place in electrical system of this? In electrical system of this, change electric current, and we see this at once. So this is a real-time virus, for example, for coronavirus or some other. How can we make such a beautiful device? For this beautiful device, this must be a bottom-up nano assembling technology. Up to now, there is, for example, how we must deal with some nanowire. How we deal with nanowire? By, for example, electric field direct assembly of nanowire, this one, or fluid flow direct assembly of nanowire, or some milk blood jet. All this technology based on fluids. Fluids are not ordered condensed matter. This cannot be compared with a bottom-up, top-down lithography, what is very, very exact. And that is why this is challenges, this is problem. And we have want to have, especially bottom-up nanofabrication, for example, like it is done in microtechnologies. And this is our goal. And for this, we must use five steps. For example, by producing of such nano device that will be also, like in previous slide, done like in micro-mechanical technology. At first, to tailor nanomaterials, this is not a problem. There is a lot of them. then to passivate or make functionalization of these devices. For example, in case of sensor for coronavirus, this might be antibody for coronavirus, or for Zika virus, and so on. Then to cut material inside components, individual components, individual nanowires. This is, for example, like this zinc or nanowire, and with functionalization for special virus, for coronavirus, for Zika virus, for dengue virus, and so on. And after this, to fabricate from this individual nanowires, special nano devices. And then to link, to integrate this to macro world, because if we see only, if we have only nano device, we must also go some connection to macro world to communicate with this. And first problem of this, what we do manipulate by manipulation, we must do something with this. For example, manipulate by small, maybe insect, we can using some insect, then going bacteria, this is more problematic, and viruses and some other is more problematic. And for this, we offer special nano tweezers that is very small. This is a sensilla or hair on the leg of the mosquito. So this is this can also cut viruses by enlargement. This is this sense. This is this nano gripper. This is very small. This is a nanometer long in Z, some micron in X and Y direction. This beautiful device is done by a shape memory alloy near thermoelastic magnetotic phase transition in nickel 2, titan 2, nickel cuprum alloy. This alloy undergo austenitic to martensitic phase transition from cubic cell B2 to orthorhombic B90 and to orthorhombic white. By this way, this is change of this crystallic structure goes to change of shape and enlargement of the sample. We can now we can see. I hope that we can see videos. Un moment. Sorry. I must show screen. Oh, yes, sorry. So this shape memory alloy, nickel 2 cuprum, this is composite, and this is shown in the screen. Shape memory alloy have problems. They need photos. They have particle effect, and they have long response of time. And now we see real time how to work this alloy. So we have solved all these three problems, and by this way we can use this for a special application. And this is also, and this is the smallest in the world nano tools. This can pick up, place, cut, pull, bend, tool, every object with enlargement from some micron up to 1 micron, some nanometer up to 1 micron. And next, yes. And how we use this is very small, very small device. This is nano gripper or nano tweezer. And how can we use this? For this, we use specially nano position system or nano manipulator And this micromechanical device, this nanotube, is on the end. This is end effector of this nano manipulation system. I have problem with go to the next slide. How to go to the next slide. So this is like in bionic. For example, elephant. Some elephant in India can make painting, and in this case, this nose is used as nanomanipulator, and there is two fingers. They are used as an end effector. Nearly by the same working also our manipulation with end effector. This is view of this nano tweezer. This is micromechanical, this end effector. Of course, we can see this by eyes, but this is a view. This can be integrated with standard Kleindick nanomanipulator or OmniProbe or many other. Temperature control using semiconductor laser or electric current. And this is a view of system together with my electronic microscope or ionic microscope. So now let us look a film about this device. This is Terminator 2. This is a real experiment. This is as a picture, but this is real experiment. So, and here is shown a manipulation of carbon nanotubes inside ion beam microscope device. This our shape memory alloy nanotools don't need engine, no transmission, and operating is very simple and cheap. Only press the button. And here we see this nano gripper. This is forest of carbon nanotubes. And this is take this and bring to anything place ever you want. For example, to some substrate. This is some bundle. And bring to some substrate where we can deal with further and make, for example, some nano devices. This is substrate, and micro change all the time. And because all the time change focus in film, we see this also very quickly now. And especially this is beautiful. I like this very much. This is, you see, that nano gripper, this nanowire, this carbon nanotubes, and this is because of very great fundamental physics. This is Casimir forces. And this is handling of whisker, and this is handling of graphene. This is bringing graphene to some other substrate for making some nano devices. And this is nano gripper for the first time give possibility to operate to enclose volume of several cubic micron. And to deal with a very, very small object. For example, this is sensilla or hair on the leg of the mosquito. Usually in nanotechnology, it is spoken about comparison with human hair, and this is a hair or sensilla on the leg of the mosquito. So nanotwizard take this sensilla and nano this bring to some substrate to study this or to make something with this. And this is also this is a process of removing this hair. This is preparing exactly this. So, and now we show by the same way is preparing of carbon indiphosphor nanowire field effect transistor. This is nano gripper, this is nanowires, and this is nanowire. This gripper take nanowires. We see. Place on contacts. Place on contacts. Place on contact. Many nanowires, but we need only one. This is contacts. This is again many nanowires, many attempts. We try, and we have success. This is exactly nanowire with functionalization over the contacts, which can be measured change of electric current when some virus is flowing through microfluidic or nanofluidic system. And we see we have success. And this is basement of this nano tweezer. And we show this indiphosphor nanostructure for sensor for individual bio nanovirus. This is how we have done this. And okay. And this is change of electric current. Maybe I am already on time, out time. This is also manipulation. This is this can be used in parallel. This can be used in parallel for mass production in future. Such technology, and this can be used for different microscope, nearly for all microscope. And what shall we offer for virusology? We can offer for virusology, for example, theranostic. This is a place of viruses and analytic or some therapy inside an array of nanowire. By this way, we can very quickly make diagnostic of many mutations of nanoviruses. Then we can measure parameter of individual nanoviruses. We can study virus-host cell interaction and study genomic of single viruses by capturing one virus, a study genome. And this is all new. Also, this is possible to use with carbon nanotubes. And conclusion. The new composite shape memory alloy nanotool can is record small and nano tool. Composite and nanotweezer provide manipulation of carbon nanotubes, nanowire, nanobio-object, viruses, and can produce nanodevice. This new nanomanipulation system open up horizon for frontier, bottom-up nanoassembling for nanobiosensor for viruses and many other nano objects. Thank you for your attention.
Thank you, Dr. Svetlana. It was an informative presentation. Is anyone having any questions?
Excuse me?
There is a difference between detection and identification and water with nanobiosensor. Yes, there is such difference because for water we use a microfluidic system, and for air we use some other systems that is already in progress. Some other question, please.
Okay, is anyone having any questions? Okay, I think there are no. Thank you once again, Dr. Svetlana. So
Thank
now
you
we
for
will, so now we will move towards the next presentation, and it is from Dr. Maria Carmen Blanco Lopez from University of Oviedo, Spain. Hello, Dr. Maria. Are you ready with your presentation?
Hello, yes, thank you. I'm ready. Yes, I'll try to
Okay.
share my screen.
So, yeah, I have making the presenter. You can click on the screen button. That is the third button on the bottom of your screen and can share your screen.
Yes, but I think I need to give acceptance somewhere in
Yeah,
my,
yeah, you need to give the permissions.
and where is this? Okay. And is it ready now?
No, it's not visible.
Accessibility. I'm giving, I don't know where to give them.
When you click on the button that is share your screen, what the screen you are getting like
Yes,
you
but
have given.
my computer is a Mac and it's asking me to change the privacy and safety of the computer, and I cannot find where to do that. Camera. Microphone. PowerPoint. Okay. Let me check now. No, it's not working.
Oh, is it asking for any permissions?
Yes, but I cannot find them. There was no possibility to do any trial or anything before, and I don't know. Seguridad y privacidad, preferencias. No, I don't know where to find this now.
Okay, so I can do one thing, like if you don't find the settings, so can you mail us your presentation so that I can share my screen? You can explain from your side.
Well, okay. Okay, I'll do that.
Yes. I will just type my mail ID in the chat box. Please allow me a few minutes.
But there were some animations that I'm not sure. Well, okay.
Or if you need time, then also it's okay. Like I can give the next presentation if you need some more time, or I can play your presentation. Is it your choice totally?
Okay, I'll send you now the presentation.
Okay, did you send to Lisa, like to the program manager?
Okay. I'm opening the email. Just a moment, please.
Okay, no problem.
Yes.
Just let me know once you send the mail so that I can download it from my mail ID.
Okay, I think it's ready. Okay, I have sent it.
Okay, just allow me a few minutes. I will download it and it will play from my end.
Okay.
Dr. Cameron, is this the PDF? Like I just received the PDF of your presentation. Shall I start with that?
Yes, yes.
Okay, thank you. Yeah, now I'm sharing my screen. Yeah, yeah. Is it visible?
Yes, yes. Thank you.
Okay, you can start your presentation. And
Thank you.
whenever you say that you have to move forward, I will move forward.
Thank you. Thank you, Jessica. Yes. Well, my name is Maria Carmen Blanco Lopez, and I am Associate Professor at the University of Oviedo in Spain. And I'm working also at the Institute of Biotechnology of the university. I teach regularly courses on analytical chemistry and biosensors. Next slide, please. we can notice that in the last years of the 20th century, the analytical instruments have grown a lot. They have gained complexity. They have modules, diverse pumps, valves. These are just some examples. Next slide, please. At the same time, there are new tendencies in analytical devices, like the sensors for glucose sensors for the diabetic people, and some sensors combined with mobile applications, or even tattoos or wearables, different devices on wearables. The idea behind all these new designs is to empower patients with the control of their illness and also to reduce the cost of the national insurance health system. Next slide, please. The World Health Organization has is developing now a program called One Health that involves many aspects on environment, animal diseases, food safety, and human health. We are all related with this concept. Everything that happens to the environment or the animal kingdom could alter the systems and also to bring diseases to humans. And in all these fields, there is a need also of these new, portable, simple to use devices. Next slide, please. In fact, the 21st century has started with this pandemic, with the coronavirus that has really challenged the whole world, has challenged all of us, this pandemic situation. Next slide, please. From the World Health Organization, the recommendations to tackle these problems are clear. Test, test, and test. Next slide. Fortunately, we have the PCR system to control the pandemic in all the countries, but these are central services and people need to queue to go to the hospitals and get the test there in situ. And this is, in fact, this is a crisis of the health systems of all the countries. Next slide. The only option, alternative option to the PCR test in the hospital are these immunochromatographic tests or lateral flow immunoassays that can be, well, they have been developed for virus detection, for the antigens of the virus, also for antibodies. However, there are some concerns about their extended use to control the pandemics. These concerns come from limitations on sensitivity and selectivity. So this makes us think if we have all the analytical devices that we need. Both aspects, sensitivity and selectivity, could be improved with the use of novel nanomaterials. Next slide, please. The World Health Organizations have released also some characteristics that the new devices or the ideal diagnostic devices should have. They can be, they are here, but they can be summarized with this acronym, ASSURED. The A is for affordable, sensitive, with a low number of false negatives, specific, with a low percentage of false positive, user-friendly, rapid and robust, ideally equipment-free, and deliverable to end users. So it can be used in any country, even in countries under development. Next slide, please. One example of these devices is the pregnancy test that everybody knows, and now the new coronavirus antigen, the coronavirus test for antigens. And in both cases, just the information about positive or negative is really all that we want, not all that we need. But if we want to use this design and develop the new devices based on this design, we need to add information also about quantification. That's important for other biomarkers and also to extend the use in other areas like food safety. Next slide, please. So the tools that we have to improve the test come from the materials field. In this slide, we can have an overview of how the materials in every period of the history have conditioned the type of well-being that the society was having. If we go to these first images, we can think about the Stone Age, Copper Age, Bronze Age, Iron Age. So in this period of the history, we name the years, the period, the age by the name of the material that was important in that moment. We do now a big jump to 18th century, 19th century with the discovery of the steel that has enabled the cars, for instance, or kitchens have also changed a lot with the new materials. Plastic is a new material that was a revolution in society. The discovery of the aluminium made possible also the planes. There are new fabrics now with new polymeric materials and also new materials for electronic devices and even nanocapsules and nanomaterials involved in drug delivery. So really, we can see that our society has a different quality of life depending on the materials that are available to cover our necessities. Next slide, please. We could say now that we are at the age of nanomaterials, and there are a series of nanomaterials that could be used to cover also our necessity. And these new nanomaterials have sizes that make them suitable to interact with viruses, because these materials have typically sizes below 100 nanometers, and this is the size of virus, antibodies, or different biological entities, and much smaller than bacteria, for instance, or cells, even cells. So we have new particles, and we can also make progress with new measuring principles, new techniques to detect recognition of events. Next slide, please. The basics for the design of the biosensors that I'm going to present here is the lateral flow immunoassays. These tests are based on immunological reaction between antibodies that are represented here like this Y shape. These are two antibodies that can bind the antigen, the blue circle here, and then we have a way to detect this chemical reaction through a label that we put in one of the antibodies, the detection antibodies. For the typical immunoassay, this is normally an enzyme that produces a color or a spectroscopic signal, and these tests are normally carried out in plates with 96 wells. But for this immunochromatographic test, we move this test to a membrane, a nitrocellulose membrane that has advantages as a three-dimensional network, easy to modify, and here the fluid moves without the need of pumps, just due to capillarity forces. Next slide, please. Typically, this have a membrane where we put the antibodies, and then we couple different other elements like a conjugate pad, a sample pad, and absorbent pad. All of them, they are ensembled on top of a plastic car. Next slide. These tests are easily commercialized. Well, I had some videos here, but it doesn't matter. We'll go to the next slide, please. We apply the sample at the sample pad with the analyte, the compound that we want to detect, and as it moves through the strips, it can react with the detection antibody that is labeled to normally gold nanoparticles. Then they move all together through the strip to the test line when there is a capture antibody that keeps and on that area of the membrane the target analyte, and then the excess of this conjugated antibody reacts at the detection at the control line, and the rest goes to the end to the absorbent pad. So we can improve the limit of detection of these devices by changing the nanoparticle. And if we want to quantify, we can also couple different transducers, different physicochemical principles on top of this test line to get possibility of quantification. All of that by changing the nanoparticle. Normally, for this red line that we can easily see with the eye, we use gold nanoparticles. Next slide, please. So we can change the typical gold nanoparticles by other ones that have different properties, like silver nanoparticles or superparamagnetic iron oxide nanoparticles, that I'm going to call them with this acronym through this presentation. Next slide. The extracellular vesicles are a new biomarker with a lot of interest. They are produced, these are a small vesicle produced by all cells, and the small part is called exosomes, the medium size is called microvesicles, and they offer new possibilities in medicine and diagnostics and therapy. They are the key for the cellular communication. Next slide. In fact, the Nobel Prize of Medicine in 2013 was awarded to the doctors that discovered the regulation of this vesicular traffic, this intercellular communication traffic. They found that the many proteins and nucleic acid were encapsulated in these nanovesicles that could travel through the biological fluids to the target cell. And any disruption in this system was related to neurological, tumoral, or immunological diseases. So they offered a way to do a liquid biopsy. By analyzing these vesicles that are in the biological fluids, there are possibilities to diagnostic and a new range of illnesses. And also there are possibilities for therapy to try to encapsulate the novel drug or the novel therapeutic principle inside the vesicles, and then they will move and travel to the target cell. The limitation to use this new revolutionary principle is the lack of technology to get information about the number of vesicles and the characterization of their biomarkers. Next slide, please. So these cells, they have a series of proteins on the membrane. Some of them they are common to all the vesicles, the transpanins, but there are some other proteins that are specific for certain pathologies. And inside the cargo has also nucleic acids like microRNAs and also other proteins and other chemical compounds. Next slide. In my research group, we have been studying the techniques that could be used to quantify those vesicles and get information about them. And we have published a review paper where we analyze the state of the art of this situation. There are mainly instruments that are benchtop instruments, like the nanosite, that detects the vesicles through the nanoparticle tracking system, or this other one, the ISON Q Nano system. They are all benchtop instruments. They have a high cost and they need training to be able to use them. Next slide, please. The other alternative is to do this ELISA test that require also an instrument for a central laboratory, and they need training. But this is very popular and is available in many biological or biomedical laboratories. And our project was to move this test to these lateral flow strips. Next slide, please. So that's what we did. We immobilized the antibody in the test zone, and we optimized all the characteristics to get the sample flowing and trap the vesicles here at the test line. We use at the beginning the combination of these tetraspanines and proteins for detection and capture. Next slide. And well, we use gold nanoparticles for the labeling system. And this picture shows the different strips, the test line of different strips with different concentration of extracellular vesicles or exosomes, and how the color increases with the concentration. Then we use, at this moment, we use a program for optical density to analyze the optical density, the image J, and get this semi-quantification or this quantification of the optical density of the line to be able to estimate the limit of detection, that in this case was around 8 multiplied by 10 to the 5 extracellular vesicles per microliter, with a limit of detection around 1 picomolar of extracellular vesicles, just with eye detection. Next slide, please. Well, this would be the way that the system works. We put the strip on the test tube with the sample, the running buffer, and all the reagents. The test line, we have immobilized, for instance, this antibody, anti-CD81, and we have also a control line. Next slide. Well, this is everything that is here in the test tube. And we add the detection antibody with the nanoparticle. Next slide, please. And well, this was an animation. Well, at the end, could we go back, please? Just a moment. I think the PDF has not kept the last part. So this at the end. No, please, back, 2 slides back, please.
Is this one?
Another one, the one with the strip. This one, please. Yes. Okay. So finally, here the detection antibody reacts with the extracellular vesicles, and as they move through the strip, they are kept here on the test line. That was an animation, but showing that part. It doesn't matter. We continue now, yes. Okay, next slide, please. We have published this work in the paper on in the Journal of Extracellular Vesicles, and also the adaptation. We have adapted the protocol to do all the analysis from the moment where we isolate the vesicles in the biological fluids, in plasma and urine, from the isolation of the vesicles to the final detection in this other paper on the journal Biosensors and Bioelectronics. And in this one, we have also developed multi-detection strips by adding different test lines. Next slide, please. We have applied this design to the detection of extracellular vesicles. in patients with other diseases that lack at present a biomarker like the chronic fatigue. And we have found that the strips were used to differentiate healthy controls from the patients in terms of size and also concentration. We could differentiate the two groups in this case. Next slide, please. And in the case that one of the biomarkers of the vesicles can be related to a specific disease, the strips can also be adapted. This was the case of the mica ligand on the vesicle surface that can be related to melanoma. In this other article, in the Journal of Nanobiotechnology, we have adapted the design to the detection of melanoma extracellular vesicles. Next slide, please. If we want to use different transducers, we can change also the particles. In this case, we have used silver nanoparticles that we synthesize through this seed, making silver seeds to grow, and then we have conjugated them with the detection antibody, and we have applied them to an immunoassay, in this case for pneumolysin. Pneumolysin is a toxin that produces, that is normally used for the detection of the pneumonia. For this work, we have developed a system based on 3 staples inserted on top of the strip. We got a patent for on this device. We could detect then the silver from the nanoparticles by using anodic stripping voltammetry. This was part of the work was developed by the PhD student Lucia Blanco. Next slide, please. And then we can use also combination of different metals in the nanoparticles. These nanoparticles that had a gold core and a silver shell, and they were useful for surface enhanced Raman spectroscopy. We adapted the test of pneumolysin with these nanoparticles. Here we can see the density of nanoparticles on the test line. As the concentration increased, the density of the particles here could be seen brighter. The control line was always the same. And we have coded these nanoparticles with a compound that was enhancing the Raman signal. We published this paper in the journal Nanoscale, and in this case we got the lowest limit of detection with these strips. That was 1 picogram per milliliter, 1 picogram of pneumolysin per milliliter. Next slide, please. And finally, I'm going to talk a little bit about our work on magnetic nanoparticles. Michael Faraday and James Maxwell study the relationship between the magnetic fields and the electric fields, but at the time they couldn't study the effects of magnetic nanoparticles because they were not known magnetic nanoparticles at that time. Next slide, please. My colleagues in physics, Professor Montse Rivas and José Carlos Martínez, they studied these effects that had these superparamagnetic iron oxide nanoparticles when they were intercepting a conductor with an alternate current. These magnetic nanoparticles have momentum that changes continuously at room temperature in all directions. And when they intercept this alternate current, these particles produce eddy currents that create an increase in the impedance of the circuit. and they found that this impedance was proportional to the number of nanoparticles. Next slide, please. So then the next step was to use those nanoparticles bound to the antibodies and use them in the immunochromatographic strips, in the lateral flow strips. They have adapted here the system to scan the strips, and as we scan the strips through the electrical conductor, we get two peaks. The first one here corresponding to the test line, and the second one to the control line. These peaks correspond to the increase of impedance due to the nanoparticles. And we can, by integrate the peak, get the area and plot the signal versus concentration. Next slide, please. These magnetic nanoparticles have a special advantage because they can be used for preconcentration. If we add them to the tube where we have the sample and the particles are attached to the specific antibody that is going to bind the analyte, then we can get a separation. We can use the magnet here to keep only the specific particles attached to the analyte, remove the rest of the matrix, and stay only with the analyte. And then we can use this on the strips. We have published this paper on the diagnostic journal and was chosen as the cover of the special issue. It's part of the thesis of Amanda Moyano. Next slide, please. These magnetic nanoparticles, they can be used just for visual detection, like the gold nanoparticles, and also they can be used for this specific magnetic quantification with this magnetic reader. Next slide, please. We have been trying to find the best magnetic nanoparticles for these purposes. So one type of nanoparticles that was successful for visual detection were these, we call them nanoflowers. They were these nanoparticles having different nucleus coated with a carbon film, and we use them in the strips. Next slide, please. With these nanoparticles, we could detect the extracellular vesicles and measure even directly in plasma from patients. And we could, well, this is the relationship between concentration and signal. And with these nanoparticles, we got a limit of detection very similar to the gold nanoparticles. And we found also that they were very useful for the magnetic separation. We could separate the specific extracellular vesicles from the rest of the components of the plasma in only 2 minutes. Next slide, please. We are now developing a project on the detection of specific biomarkers for colorectal cancer. These biomarkers are also located in the extracellular vesicles. And we have already compared the capacity of the magnetic reader and the optical reader, and we have found, well, that the limits of detection in both of them, they were very similar. So we have collected 250 samples in collaboration with a local hospital here, and we are processing all these samples, trying to see the degree of success of the detection of these biomarkers and the correlation with the medical history. Next slide, please. Well, this is the last paper that we have published with this first study on this proof of concept with the colorectal biomarkers in the journal Sensors. Next slide, please. Well, and we have published the principle of the magnetic reader in this journal, in the journal Analyst, and also some other applications on the detection of prostate-specific antigen in the journal Biomagnetics, and also a state-of-the-art on the synthesis of iron oxide nanoparticles for biosensing biosensing applications. Next slide, please. And finally, we wanted to see if this sensor was useful for detection in the food science field. We chose the target histamine, which is related, it's a compound produced by bacterial decarboxylation. It is produced in fermented food and also in fish, but for fish it means that the fish is in bad state. And this compound is related with food allergies. It has toxicological effects for people, especially sensitive, with specific sensitivity to the histamine. They need to control this concentration in food. And it's also interesting in wine technology, in the wine industry, because it spoils the organoleptic quality, and it's also a matter of quality for commercial transactions. Some countries have restricted the wines that they import depending on the content of histamine. They have established thresholds for the commercial transactions. Next slide, please. Well, this would be the test for the histamine. In this case, we put histamine here on the control line. The histamine is also in the sample. Next slide, please. And then we add the antibody here, and the antibody needs to compete with the free histamine and the histamine that is immobilized in the sample. So finally, we get a red line or a brown line here on the test line, and the excess goes to the control line. So in this case, where there is no histamine in the sample, we'll have the line, all the antibodies here attached, and then we'll have the full signal with no histamine. And when there is no histamine, when there is a lot of histamine in the sample, there would be nothing really attached here. Next slide, please. And finally, we reveal the test by adding protein G that binds specifically to the end of the crystallization fragment of the antibodies. So this is an example of the strips. This one here, the one that has the two lines here, is the blank of the control, and as the concentration increases, the line decreases. Next slide, please. And this is, well, the plot with the concentration, the relationship between the signal and the concentration with both the optical detection and magnetic detection. In both cases, the limit of detections were very similar. Next slide, please. And we have published this work in the Journal of Analytical and Bioanalytical Chemistry. Next slide, please. Well, we are applying now these principles in this new project that we have with, is related to the detection of biofilms. It's a Marie Curie action, a European project that involves all these other universities and these companies here. Next slide, please. And this is, well, finally, I would like to thank all the members of my research group, all the finding societies, and all of you for your attention and your patience at the beginning with these technological problems here with the presentation. Thank you.
Okay, thank you, Dr. Maria. It was a good presentation. Is anyone having any questions? Okay, I think there are no questions. Once again, thank you, Dr. Carmen.
Thank you.
So now we will move towards the next presenter, that is Dr. Zohra Ali Gabriel from University of Sabarta, Libya. Hello, Dr. Zohra.
I cannot switch off.
Hello, Dr. Zohra. Am I audible
Hello?
to you?
Hello,
Yeah.
yes, I hear you. Yes.
So
Hello?
I'm going to make you the presenter. You can start your presentation.
Okay, I will try to start my presentation if I can on my
Okay, just a
computer.
minute.
Okay.
Yeah. Yes. Now you are the presenter. You can share your screen and start your presentation.
Yes, I share now.
Yes, now it's visible. You can start your presentation.
الشاشة نحطها تنقل نحطها هي. Just a moment, I try to start.
Okay.
ده المفروض مش عارفة أعمل شغل. Now I think everything is going to be well.
Yes, you can start your
Yes,
presentation.
yes. Good afternoon for everyone. I am Dr. Zohra Ali Jibril from Faculty of Science, Sabarta, from Libya. Today I am going to present my work, which is under the name of Transport Properties of Lanthanum Calcium Manganite with Heavy Thin Doping. Introduction. Perovskite manganite, which named as lanthanum manganite, where A is calcium or strontium or barium. This material has a big interesting from the researchers from the last few years. The hold of perovskite manganite with this general formula have been studied extensively because for the interest in these materials related to the great magnetic properties such as CMR effect and MC effect. The MR is has very large application in technology such as a magnetic data storage and read. This perovskite has a thrombus structure this material used in magnetic mini magnetic device technology such as the magnetic data storage, read-write magnetic, and magnetic tunnel junction MTG, and another application. And this is a change in phenomena related to the double exchange mechanism which happen in manganite transmission. In this work, we are going to interest in this phenomenon, and we try to prepare a bulk polycrystalline when we substitute tin in lanthanum side with different concentration from zero point 0.1 and 0.2, 0.3, and 0.4, where this material is prepared by solid state reaction, SSR method. The CMR, there is two types. One, on applied external magnetic field for a sample, electrical resistance notes by increasing. The another one, on applied external magnetic field for a sample and topped hole electrical resistance notes by decrease in the phase change from paramagnetic to ferromagnetic. Here, this is paper is focused in this part in CMR. Closure magnetoresistance is defined as it's the property of some material which has electrical resistance changes by order in magnitude when external magnetic field is applied in this material. The ratio is calculated by this equation where RH when a magnetic field is applied, R0 resistance without magnetic field. This article actually choose Sn to substitute in lanthanum manganite in lanthanum side for two reasons. On one hand, Sn has a certain magnitude about 1.5 newton. On another hand, the ion radius of Sn is smaller than lanthanum manganite, which Sn is about 0.7 angstrom. Hence, the lanthanum is 1.60 angstrom. Experimental. Actually, the experimental was done by solid state reaction. First of all, we are mixed the lanthanum oxide and tin oxide with the calcium oxide and manganese carbonate with acetone. When we calculate in equation the ratio between these oxides and put it in a milling machine for 24 hours to be sure we are making a homogeneous mixture. And then we dried this mixture and calcined it at 900 Celsius for 12 hours. After that, this mixture was grind and saving to be sure when done the centering every grain is very, very small size. That's why we are using a saving about 13 micrometers. After that, we put pressing the powder when made 1.2 gram as a pelt and the pressing in 6 kilo Newton. And finally, we follow the centering process, which was in flow oxygen at 1300 Celsius for 24 hours in air. The measurement equipment was used for the final powder for all the samples. First of all, we checked the structure for the samples by using the X-ray diffractometer. It's Philips X-ray diffractometer with the lambda 1.5 angstrom. The data was collected from 10 degree up to 100 degree. This is the angle with setup size of 0.002 with step. Continue for all the steps. And then we see the microstructure by using the scanning electron microscopy to see the morphology of the sample and the fraction surface of all the sample. Then finally, our area interesting is magnetic properties was used to check the CMR effect by using a magnetometer where the temperature range from 19 Kelvin to 300 Kelvin and a maximum magnetic torque is 1 Tesla applied. Result and discussion. Here we are going to show our result. First of all, we are showing the X-ray pattern for all the samples. The X-ray pattern were collected at room temperature using the diffractometers with Cu K alpha radiation. Lambda is about 1.5 angstrom and at 14 kilovolts and 13 milliampere. The powder sample were scanned in range to theta from 10 to 18 degrees. 18 degrees. The X-ray diffraction show here all the samples is pattern all exhibit the same with the pure sample, and the crystalline structure is an orthorhombic symmetry. The pattern were analyzed and the peak is checked operation for H and KL reflection, followed by extinction rule of reported spacing group is 26p in MA for all the samples, and all the samples actually in one single phase material. As seen here, where as concentration increase, the intensity of the samples is increased with each WFM becomes smaller for all the samples. We collected from the X-ray diffraction the lax parameters of all the sample A, B, C lax parameter and unit cell value as shown here in table. In this table, as seen from this table, all the samples as the concentration increase, the volume of unit cell is decreased because we are replacing thin, which is smaller, ionic radius. After that, we are to see the grain size. As seen here from this table, the pure one is about, the volume is about 229 angstrom, and for the high concentration is about 226 angstrom. The CMI image for all the sample is coming electron microscopy. The pure sample, which was in very, very small grain size, and average size is about, the magnification is about 2000. Although all the particle size greatly varies in a broad range from the nanometers scale and few of micrometers scale. The samples that have been subject to this study consist many of small particle nanomaterials order, and the most of these small grain have nearly spherical shape. The scanning electron microscopy of all the sample showing the grain size is becomes increasing with the increase the tin concentration. With the substituted of tin, the grain size is increasing. as seen from 0.2 is more than the grain size is more and more fully than pure 1. As in 0.4, the boundaries was very close and the distance between the grains it actually is very close and the grains is bigger. Then we are calculate the CMR ratio as defined in MR ratio by using this equation. We use the magnetometer for probe devices and we calculate the CMR. CMR on the sample has the maximum ferromagnetic Curie temperature is absorbed for all the sample. For 0.1, the Curie temperature is about 68 Kelvin. When the doping level is increased to 20%, Tc is around 78 Kelvin, which below this temperature, the material show metal to insulator. This is the phase transition temperature. And after and the magnetic properties of these manganite have been described using the double exchange mechanism between manganese ion 3 and manganese plus 4 ions. And also it is very described tangential effect and Zimmer theory. The closer magnetoresistance and unusually large change in resistivity is absorbed in this material when applied magnetic field, which was about 1 Tesla. The CMR for this material is various sensitively with the changing of Sn concentration. This can be achieved by introducing trivalent rare earth ions of different size ions and perovskite structure. We find that closer magnetoresistance effect is low Tc system can be explained by transport from paramagnetic demons. This is depend on sensitive on relative spin orientation of paramagnetic demons, which can be controlled by applied magnetic field. Conclusion. In this study, we substitute the tin of lanthanum manganite, which has the smaller ionic radius. This effect show the paramagnetic transmission to paramagnetic phase. X-ray diffraction show all the samples are the single phase and in orthorhombic structure. Also, X-ray diffraction show as concentration of Sn increase, the unit cell value decreasing because the ionic radius of Sn is about 100.113 nanometers compared with lanthanum, which about 116 nanometers. All the samples show decreasing in antiferromagnetic ordering temperature with increasing of substitution increasing. Magnetic measurement indicated that the temperature decreased with increasing of tin concentration. In this study also, the effect on the samples exhibit decreasing on antiferromagnetic and the ratio all the samples CMR around its phase transition temperature. Thank you.
Thank you, Dr. Zohra, for your presentation. Is
Okay,
anyone
I hope
having any
everything is
questions?
going to be okay.
Is anyone having any questions? I think there are no questions. Yeah.
Just can I? Hello.
Yeah. Hello.
Hello. Hello.
Yes. Can I ask one question?
Yes, you can ask.
Zohra, thank you very much for interesting presentation. Just asking about application of such materials.
Yes.
What you see the application of such magnetic materials?
Yes, you are asking about the applications of this material. This material is interesting in this cinema because they can use in many magnetic devices as hidden devices in computer and sensor device because we are trying to reducing the transmission temperature.
Yeah. Thank you.
You're welcome.
Okay. Thank you. Is anyone else having any questions? Okay. Thank you once again, Dr. Zohra.
Thank you for
Yeah.
your. Thank you.
Thank you. So now we will move towards the next presentation. It is from Dr. Olga Kiselyova from Moscow State University, Russia. Hello, Dr. Olga.
Hello, nice to see you all. Can you make? I can't run my screen.
Yeah, I'm making you the presenter. Yes, it's done. Now you can click on the button screen and share your screen with us.
Oh, there it is. Good. Just let me open it for myself. So share. So can anyone see the screen?
No, it's not. Oh, yeah, it's visible now.
So
You can
see it now.
start your presentation.
Okay, let me just make it in form of a slideshow. Just a second. Okay, let's talk a little bit about biology now. I work in Moscow State University, but together with some people from the first medical institute. And we are working on different biomedical materials, and our primary interest is bacteria cellulose. So today I'll talk about its purification in supercritical media. And in the end, I will stop at some structural aspects of this material. First of all, let's see what is bacteria cellulose. So, and why is it important to study it and how it can be used. What's the difference between bacterial cellulose and plant cellulose? Actually, bacterial cellulose is a unique material because it forms a pellicle, or you can call it a membrane or a film, whatever you like, and it consists of entangled cellulose fibers. And they are very thin, like 30 to 100 nanometers in diameter. And as one can see from its name, some authors also call it microbial cellulose. It is produced by prokaryotic organisms, mainly gram-negative bacteria. And the best known of this bacteria is Gluconacetobacter xylinus. There are a lot more other strains like Acetobacter, Agrobacterium, Pseudomonas, etc. I cannot name them all. And they all are cultivated by biotechnologists, and it's a very fast growing field of biotechnology now. Just like plant cellulose, bacterial cellulose is a completely extracellular substance. Why do all these organisms produce bacterial cellulose? In fact, we don't know, but we believe that it creates a raft that lets these bacteria float on the liquid-air interface so that to access atmospheric oxygen. All these organisms absolutely need oxygen. It's essential for their metabolism. If they get into some conditions where there is a lack of oxygen, they no longer produce cellulose, they don't produce anything, and they just exist in the inactive form. So you have probably seen bacterial cellulose on the surface of maybe some wine or juice that has been left for a while, and there is a white pellicle on top of it. Be sure this is bacterial cellulose. If you look into scanning electron microscope, you will see not only the gel, I mean these are the cellulose fibers, and you will see bacteria. These are the guys who produce this material. What is the main difference between bacterial cellulose and plant cellulose? See, all these properties listed here are extremely important because they make this material really valuable. First of all, bacterial cellulose is very pure. If you extract cellulose from plants, you will, apart from cellulose, also have some hemicellulose, lignin, pectin, etc., some other polymers. Bacterial cellulose is chemically pure, so you don't need any chemical processing to get rid of these other polymers. In the second place, the fibrils themselves are much thinner. They are actually nanofibers, and they do not aggregate unless you dry them in ambient conditions, but that's another issue. This cellulose also has a much higher crystallinity, like 80 to 95%, and that really improves their mechanical properties. Another very important issue about bacterial cellulose is that it is a natural physical gel. It means that from the very start it exists in the form of a gel. Lots of effort has been actually spent for trying to make gels out of plant cellulose. And to do that, we need to introduce some cross-links between cellulose fiber, and that needs chemical treatment, effort, etc. In case of bacterial cellulose, you have a gel from the very start. And this gel also has a very high water holding capacity, up to 100. If needed, you can turn it into xerogel or aerogel. It's also a low renewable material with very low costs of raw material. And it also can be produced from food industry byproducts. We don't do that in the lab. We use chemically pure methods, but when it comes to production, to mass production, of course, it's very good that you can use waste products. Bacterial cellulose can be used in pure form or in form of composites with other bare polymers or inorganic fillers, including nanoparticles, metal nanoparticles, and hydroxyapatite, whatever else. There are the good news about bacterial cellulose, but there is only one bad news about it, that it needs purification. If you want to use it for some technical applications, like making paper, making acoustic membranes, or making some filters. This is not really obligatory, but when it comes to biomedical applications, which are really numerous, it's making wound healing materials, making scaffolds for implants, blood vessel grafts, tissue engineering grafts, hemostatic materials, drug carriers, whatever else. You need to get rid of these bacteria who produce it. So these guys have to go away. There are several conventional techniques that allow for doing this, but all of them are not perfect. They are normally labor consuming and time consuming. So we need to work out something oh, sorry, just one thing I forgot is a typical procedure for preparing biomaterials is just sterilization in an autoclave. Why cannot we use this simple method to in bacterial cellulose? Because all these gram-negative bacteria, they have outer shells that contain such peculiar substances like lipopolysaccharides, or we call them endotoxins. As you see from their names, endotoxins are toxic to us animals. And if we want to this material to contact with our tissues, then we absolutely have to get rid of them. There are very serious criteria about that and requirements and regulations. If you use just autoclaves, then endotoxins will not be removed because they are very thermally stable and they easily survive this kind of treatment. So we need to think of some other methods how to get rid of them, because if we don't, they might cause fever and allergic reactions and even anaphylactic shock, which can be even mortal at some point. So the objective is this process of getting rid of endotoxins is called deperogenation. And so in traditional techniques, we first do deperogenation in alkali or surfactants. There are several protocols. And then we have to do the sterilization. Yeah, the sample has to be rendered sterile. And we needed to make a one-step process that would do both at a time. And for that, we chose a supercritical processing in supercritical carbon dioxide and sometimes using co-solvents. In that case, you can just omit the second step and do it all in one procedure. All the materials that we were studying in this research were produced by gluconacetobacter hansenii, and we use pretty standard Heston-Schramm media to do that. Also, as the main supercritical media, as I said, it was just carbon dioxide under very high pressure and some polar solvents, which are also very simple. It was just water, hydrogen peroxide, or ethanol. How do we check if we have removed the endotoxins? This is also the standard Limulus amebicide lysate test. And then this is how the bacterial cellulose pellicle looks like when you extract it from where it grows. And if you dry it, it's pretty much like this type of film. And the next slide, you can see the experimental setup that we've been using to do this purification. So, in the first steps of our research, we first tried to use only supercritical carbon dioxide, but it actually didn't give us any good result in terms of polysaccharide removal. But the good news was that after this treatment, the samples were at least already sterile. In order to improve the quality of purification from lipopolysaccharides, we added some polar solvents to it. So the easiest way was to add just pure water and into the reactor, and then add the carbon dioxide. Under high pressure conditions, the carbonic acid is formed and the pH drops up to 3.5. And then we keep the sample there for a while and let the carbon dioxide out afterwards. What do we expect to happen in that system? When there is depressurization, when the pressure drops, you get bubbles of CO2 in this medium. And since it's hydrophobic, then amphiphilic compounds, they easily put the hydrophobic parts into the hydrophobic medium, and the polar parts stay in the polar co-solvent. And this is pretty much like an emulsion, and that helps to extract these strongly amphiphilic compounds. Other solvents that we have tried, except for water, were hydrogen peroxide, ethanol, and some other not really important stuff. So did we get a very good result? Yes and no. We managed to achieve several-fold reduction of the level of endotoxins, but still we could not reach the so-called medical grade that you need to have if you want to make some really biocompatible material that you will further use on humans. But at the same time, all the samples, whatever co-solvent we use, were rendered sterile. So this method can normally be used for samples sterilization. And why is it good? Because you then avoid really high temperatures, since carbon dioxide goes into the critical state at the temperature of only 31 degrees. And it is known that high temperatures might affect the mechanical properties of cellulose. We checked the samples not only chemically by limulus amobacillase test, but we also used lots of microscopic techniques. And for example, atomic force microscopy. We checked the samples before and after processing. And here in this picture, you can see the cells on top of the bacterial cellulose. And after processing in carbonic acid, you see that the cells are still there. So we wanted to understand what really happens to bacteria in supercritical media. The first thing that we can absolutely state that these bacteria die, because the samples are sterile. Bacteria cannot live after that, but their bodies, the dead bodies of bacteria, are unfortunately still there. So we decided to see what happens to lipopolysaccharides. Are they still on the surface of bacteria, or are they spread all over the film? And that's why we see them in the chemical test. How we did that? We decided to once again turn to microscopy and compare the dimensions of bacteria. If you want to measure the diameter of a bacterium in atomic force microscopy, you better image it and measure its height, because there are certain artifacts in this technique that does not allow for precise measurements of the diameter in the lateral dimensions. But it's not a big deal, since bacteria has a rod-shaped form, then diameter is the same thing as the height. It is not easy to measure it in the film itself because, as you see from here, the surface is not flat, so you cannot correctly measure the height. So we had to transfer these cells onto some really flat surface. For that, we chose a classical substrate of mica, which is often used in atomic force microscopy. But bacteria actually do not really well adhere to mica, so we had to cover it with some polymer that would have a positive charge, and then the negatively charged bacterial surface would pretty well adhere to it. For that purpose, we chose chitosan. It's known that bacteria don't like chitosan, they don't proliferate on it, but they, at the same time, these bacteria are dead anyway, so it was not a big deal that they stick to chitosan surface. How did we apply chitosan onto mica? We also used the same setup. We just added some chitosan into the reactor and water. You know that chitosan does not dissolve in water, but when you add supercritical or at least high pressure carbon dioxide, then the pH drops and chitosan easily dissolves in carbonic acids. Then you leave it for 1 day and it pretty well adheres to mica surface. After that, you take it out and you can put cells on them. Where do we take cells? We transmit the cells from these pellicles just by pressing mica over them, or alternatively we can cultivate them on agar containing media and then make a suspension of bacteria, and once again place a droplet of them onto this prepared substrate. So how can we see what changes, yes, before and after the treatment? First of all, we compared what bacteria look like in dehydrated and rehydrated states. What we did, we first imaged bacteria in dry state after dehydration, and then we, sorry about that, added some water into the atomic force microscopy liquid cell and compared the dimensions. So we just imaged the very same picture, but without water and water. And when we see that in the presence of in liquid media, bacteria are much higher and they are much thickened. The difference is about 170 nanometers. How do we explain that difference? Mainly because we know the structure of the bacteria outer shell. Yes, the polysaccharide parts of endotoxins, they swell in water and form a gel-like substance, which is easily sensed by the tip of the atomic force microscope. This is how a gram-negative bacteria looks like in liquid media. And then when you dehydrate it, these polysaccharide chains, they just shrink and bacteria look smaller, yes? And that's exactly what we see when we compare the cross sections made along these lines. This is the explanation. So the main idea is that we totally remove the polysaccharide chains. There would be no difference between the dimensions of cells before and after dehydration. So we put the samples just with mica into the reactor and processed them in carbonic acid under high pressure. So what do we see? We see that still there is a difference in the cell's dimension, but it is not as big as it was before the treatment. So we tried the same thing with the other co-solvents such as hydrogen peroxide. So we finally got that still there is a difference, but now the difference was smaller. How do we interpret these results? We interpret that part of the lipopolysaccharide shell was removed, and now this effect of swelling and shrinking is not that well pronounced. And we even can compare which is more efficient. So in that thing, using hydrogen peroxide is more efficient. Maybe this is partially because of the fact that in the presence of hydrogen peroxide, some of the chains are just destroyed, not simply removed due to supercritical processing, but partly destroyed. But anyway, we see the difference in this effect. So another issue I'd like to stop at is a microscale morphology of the bacterial cellulose. There's been lots of publications and lots of photos in scanning electron microscopy that show the organization of fibrils. And normally, if you look at the top of the film, here is the medium with nutrients. It's a petri dish, or it can be any vessel you like. And here's the film that is growing on top of it. If you just look on it from the top, you will see something close to isotropic gels, where the fibrils go in all directions. But if you go further and make a cross section of this film, of course you have to freeze dry it first, otherwise it doesn't work. You will see a lot of more interesting things. You will see that the structure is actually anisotropic, and you can see that there are layers. Yes, it's a layered periodical structure. It consists of some fleeces, yeah, like non-woven leaflets, consisting of cellulose fibers, and in between them there are some areas where the density of the material is really very low. You'll ask me how this happens. Yes, if you say periodical structure, that means self-organization. Where does it come from? The answer is we don't know for sure yet. There is no strict theoretical explanation for that at the moment, at least to my knowledge. And we were working on trying to understand how this works and where this comes from. What do we know about how this system originates from? There's been lots of experiments done by the groups who have shown that the new lower layers are always formed on the liquid-air interface, always on the top. So the bottom layers are old layers and the top layers are new layers. And step by step, this film sinks down. There's always been some speculation that the formation of layers is actually due to stepwise sinking. But we have actually disproved this, or maybe it is due to freezing, yes, but we have disproved both these ideas. We have milled this film into paste and made photos in electron microscope, but the leaflets were still there. So it means that they formed before freezing. And if you use some other morphology, not just flat films, but if you grow tubes, then the leaflets form coaxial cylinders. So it has nothing to do with sinking, because there's in that system there is no sinking at all. So there should be some other theory beyond this. What do we know about it all? The rate of accumulation depends on many things. First of all, of oxygen availability. And when the concentration of oxygen drops below a certain limit, the formation of layers stops, and the gel is just grows isotropically. It also must be pointed out that these layers are impenetrable for bacterial cells. So between each layers, there is a zone where all bacteria are kind of trapped. They can't get out of this space. What does the morphology of the layers depend on? Depends on cultivation conditions, but there are so many factors that are included into cultivation conditions, because so many people and so many groups have worked on that, trying to get the maximal productivity. So we kind of analyzed a lot of data, trying to understand the physical nature of the factors that have some impact on the productivity, which in physical terms is the accumulation rate. Because most of biotechnologists only care to get the highest possible productivity and don't really look deep close in the structure. So what factors do we have? The source of carbon can be different. Different sugars, disaccharides, alcohol, etc. The producer strains are also numerous. The availability of oxygen might be different. The pH, the concentration of nutrients, and the source of nitrogen also changes the productivity, and even the temperature. Though the range where the producers can live and make bacteria cellulose is not high, it's just maybe 10 degrees, but still there is a big difference what temperature you use during the cultivations. How can we put all these factors together? Because they're so different, how do they impact on the inner structure? And we believe that their impact is indirect. Each of these factors has impact on the accumulation rate of bacterial cellulose. And this is the rate that further influences what kind of structure we finally get. Structures can be different. It can be an isotropic gel, which doesn't matter which side you like look at it from. And isotropic gels you normally see when you use some unfavorable cultivation conditions. That means that the bacterial cellulose mass is accumulated very slowly. If you have a very high productivity and high rate of laying new fibers, you get these layers. Yes, in this picture the air-liquid interface is from their side. And there are also some intermediate cases when we once found liquid crystal-like packing. It's, the arrangement of the fibrils is very similar to what you see in cholesteric liquid crystals. From layer to layer, the preferable directions of fibers changes. So in zone 2, it is parallel to the screen. In zone 4, it's orthogonal to the screen, and these are some intermediate angles. Why is it important? So what of these conditions is the most favorable? So what morphology should we choose? That really depends on your application. If it's a technical applications, when you need very high mechanical properties, then you'd better choose this kind of inner structure, because when you have layers, you have higher modulus of elasticity and high toughness, you get a mechanically good material. But if you want to make some composite for biomedical application, for example, then these layers are actually a shortcoming. Why? Yes, because they restrict diffusion in that direction. So if you want to make a composite, you have to introduce some, for example, polymer into that film. And I think it's evident that these leaflets, they serve as barriers, and they don't let the polymer come into the whole volume of the film. For that kind of application, you of course need this kind of gel with high permeability and high diffusion coefficient. So what condition is better depends on your application, but in it's a very complicated system. You change one parameter just slightly and you get a completely different microscale organization. Is it good or bad? I would say it's good because the nature gives us not just one material, but a whole set of materials which is chemically the same, but physically different. And what we have to learn to do is to control that and to tune this structures by using appropriate cultivation conditions. Yes, and what is appropriate depends on what you want to get, what kind of organization. So I'd like to thank you, and if you are interested in more detail on these topics, you can check to publications dedicated to these two topics of purification and microscale organization. Thanks.
Thank you, Dr. Olga. It was a good presentation. Is anyone having any questions? Okay, I think there are no questions. Thank you once again for your presentation.
Thank you.
Okay, so now we can take our lunch break, as now the time is 1:20, so we will take a half an hour break and we'll be back at 2 o'clock. That is 14 hours. Please be connected. We will be back at 14 hours. Yeah, hello, welcome back everyone after the break. So now we will proceed towards our next presentation. Hello, Dr. Nahida, are you ready for your presentation? Hello, Dr. Nahida. Your voice is not audible. Yes, yes.
Yeah. In my I have a little problem in my camera, but screen I will.
Yeah,
Hope that
I'm making you the
it will.
presenter. Yes, it's done. Now you can click on the screen button and start your presentation.
Yeah, just a moment.
Okay.
Okay. Share. Thank you very much.
Yes, it's now visible. You can start your presentation.
Yes, just a moment. Oh, but I can. I want to close this window another to because this prevent my visibility of my screen. What is?
Okay,
I
you
want
can
to.
close that and open another window or presentation, anything.
Okay, just a moment. A few seconds. I try now. Unfortunately, with my camera, I have a problem. I wanted to open my camera.
Yes,
Okay.
now you can close this if you are having problem and open the presentation.
Yeah. When I try to close,
Okay.
in this case, it asks me to leave a meeting, but I don't know how.
No, you need to know. Yeah, you just click on the PowerPoint. Leave it as it like that. Click on the PowerPoint.
PowerPoint, because you told me that it's a PDF file is necessary. If I open a PDF file.
So, do you have PowerPoint presentation or you don't have?
Yes, I have.
You can present it from the PowerPoint as well.
Yeah, just a moment.
Leave
Okay.
it the PDF like this.
There is a leave meeting to asking
No.
me.
No,
Yes.
I'm saying that
No.
please
Yes.
place the cursor on PowerPoint presentation that is in your taskbar. That click on that. Yes, click on that.
Okay. No.
Yes, now it's visible. Yes, now you can start your presentation. Click on the slideshow.
Yes, I know, but the problem is my screen. Oh, this. Oh, okay. Now.
Yes.
Now it's okay. Excuse me for. Okay. Slideshow. And okay. Thank you very
Yes,
much, organizers, for opportunity for me. And thank you all participants who listen me now. Good day, everybody. I am Nahida Musaiba from Azerbaijan. Azerbaijan, I probably some or most people knows about my country. That is Caucasus region country with rich oil, oil in onshore and offshore. It is Azerbaijan location is crossroads of Eastern Europe and Western Asia. First, I want to show you what about I will speak. I will speak about carbon nanotube based sensors. Starting from materials, from material synthesizing, I mean, and to devices. Okay, I am working at the Institute of Physics, located in Baku city, capital of Azerbaijan. And the Institute of Physics, while is an old institute, but the laboratories are rich with modern equipment and for characterization and different technologies. What about sensors? Sensors are different type of sensors almost in every area of our lives we can meet. Temperature, humidity, infrared, pressure, magnetic, chemical, color, light, and so on, gas and chemical sensors. That's many producer companies are interested so many companies are interested to produce different type of sensors. But our interest to prepare more effective and simple work, small, lightweight, portable sensor for detection, in particular nitroaromatic explosives and TNT, RTX, pattern, MEX, and also toxic gases and also dangerous gases for life. The most important parameters of characterize the sensors are sensitivity of the sensor, of course, and other parameters, that's detection limit, stability, response time, recovery time, and also selectivity is important. This is ability to distinguish searched molecules with respect with another organic compounds present in atmosphere. And also it is important working temperature, of course, the temperature that corresponds maximum sensitivity. At the present we activate on developing portable sensors for unmanned explosive detection, in particular nitroaromatic explosives that are special characteristics that they are rather low vapor pressure at room temperature. That's why it's not easy to detect such material-based explosives. That's you see in the picture, different handmade, fabricated explosives, plastic, houseable plastics, and you see here, and metallic, and so on. That are very much in our freed regions, in our Karabakh region. That is many efforts for needs for cleaning of such explosives. The sensors for explosive detection are widely very actual in present time, especially. That's why many different methods using for prepare detectors to fabricate detectors for explosive detection, especially spectroscopical methods, are very selective and sensitive and very precise detect explosive materials, especially. That's our infrared spectroscopy, mass spectroscopy, especially using ion mobility spectroscopy. That's you see here some of equipments that are mainly using in laboratories, but disadvantage is that not area using, for example, mine for mine detection underground. That is the problem, of course. Of course, there are different methods. For example, natural methods using some many useful dogs, especially, and some scientists also suggest using bee for mine detection. Especially, dogs are using for plastic housed mine. And also there are the different portable devices prepared, fabricated, and these portable devices are has many advantages, that they are detecting trace amounts or even nanograms, micrograms, or explosives, sampled in form particles or as vapor. But this method, of course, is good and indirectly detection methods. These methods in portable devices, and they are, but even they can assume that the object or person come into contact with explosives. That is the method of principle working. But some disadvantages is that they are still complex, they are expensive, they are need time analyzing for always. It's not fast analyzing, and they require expandable materials. And also it is very important that they are using manned human presence in explosive, directly explosive detection. Okay, in this case, also metal oxide-based sensors are also developed, especially zinc oxide-based sensors. That's usually we know metal oxide sensors are good sensitivity. But the one main problem with metal oxide sensors is that they are even good, have good sensitivity. But in this picture, you see that all type of the vapors, they can more or less the same sensitivity. This means that they're even they are also doped with different metals, and this is not give a good result, because this is continuing not better selectivity. This is the problem of metal oxide based sensors. What we need in this case, especially our task force, remote detection of the explosives. Not in previous slides I showed that human presence. In our aim was remote detection, not touch, not to be close to the explosives. For it's necessary to fabricate sensors with more effective, high sensitive, simple work, small, lightweight, high selective, portable, low energy consumption. I will next slides I will show why. And the important is cost effective, because all portable devices are still very expensive. Main objective for this task, we searched carbon nanotubes sensor element to detect such nitroaromatic explosives. Several years, more than 10 years, I am and my group were working on synthesizing and application of carbon nanomaterials. That is different application fields we used till now, and then we decided to use carbon nanotubes for such explosive detection, especially nitroaromatic content explosives, I mean. Because the carbon nanotubes are unique properties. Among of these properties, electrical properties are also very good. That is depends from chirality of the carbon nanotubes. They can be or metal, they can be semi-metal or semiconductor. This is good opportunity for do the sensors on the basis of it. And also there are good absorbent materials, but the absorbent, to be an absorbent, is not so good for the sensor, because if it is absorbed, but this I mean clean nanotube, if we take a clean nanotube, they can also to be absorbed some vapors around, but in this case, if we need to have a selective device, selective sensor for especially nitroaromatic TNT, DNT, and the other aromatic explosives, it needs to be functionalized. Different type of functionalization. We know covalent, no covalent, endohedral, and the external decoration with inorganic materials. But in our case, the work principle, our idea, our idea is to create amino group on the walls of carbon nanotubes, and in this case it will be electron-rich aromatic ring, and interaction with electron-poor aromatic ring, in particular TNT molecule, which lead to formation of charge transfer complexes. And if we do some network structure, in this case, between the contacts, it will be changed conductivity of nanotubes after interacting with explosive materials, molecules, because TNT is able to form for complex and acid-base pair complex. We have first synthesized carbon nanotubes and analyzed it. We use this irresolubility methods using liquid hydrocarbons, get some ferrocene, and a high temperature. We have obtained good quality carbon nanotubes, good crystalline. X-ray diffraction showed these results, and also Raman spectroscopy showed the results about good quality of carbon nanotubes. They are long, and the transmission electron microscope show that even we used ferrum catalyzers. In our case, some parts of nanotube, inner channel parts of nanotubes, and tip some catalyst ferrum, in our case ferrum catalyst nanoparticles locate inner channel and the top of nanotube. But in every case, this is before of cleaning, and if we want, we can clean nanotubes from the metals. Okay, functionalization process of carbon nanotubes. It is carried out in two steps functionalization procedure: oxidation, carboxyl groups, creation of carboxyl groups on the wall of carbon nanotubes, and amination. Oxidation is a well-known method using sulfuric acid and nitrogen acid 3.1. And amination procedure is different. We use the three different methods, and details these methods will publish in the near future in the journal. And I will show you characterization results of the first oxidated carbon nanotubes. You see here carboxyl groups on the walls, and we observed in infrared spectroscopy. This bond is located in 1724 centimeter -1. And then when we functionalized of carbon nanotubes by amino groups, some parts of oxidated groups is disappeared, and this is changed to amino groups. Amino groups you see on the walls, and when we use the in the characterization, you see here the position of the carboxyl groups are changed to amino groups. So it has disappeared and appeared this position in for nitrogen amino group, What we decided and what the results of elemental analysis show, that when we use the acyl chloride with ethylene diamine, In this case, we have nitrogen small percent. Then we use ethylenediamine via DCC mediated coupling. First, we use the 48 hours functionalization, and we have results 4% of nitrogen, and then we decided to increase the time of functionalization, and in this case we have observed a high percent of nitrogen. Here you see the peaks, XPX peaks for nitrogen. This picture also shows how the functionalized nanotubes are dispersed just in water. And after a month, we put in a stay, and after a month, its state not change, nothing. But this is a clean nanotubes. You see agglomerate of pure nanotubes. So the next, we prepared structure on the network structure on the basis of functionalized nanotubes. We use the as a substrate polyceramic glass or sapphire substrates, and on contacts we used as a contacts gold contact or silver contact, and then we use the TNT vapor for as an atmosphere 10-8. You see here during 5 seconds is react to the TNT vapor and detect it, and then a few 10 seconds is recovering. Then they use the DNT, dinitrotoluol. In this case, the same results. We have 5 seconds sharp response, and then recovering and stabilize. We have compared our results with the well-known silicon nanowire sensor in the same condition. We repeated the same condition in order to compare. You see here the author's results, and this is our work results. Expected sensitivity in 1 ppb, rise time few seconds, and the recovering time some 10 seconds. The recovering time is very important parameter for the sensors. Okay, finally we have prepared, we have made our prototype of this of the sensor. Prototype of the sensor. Here, the sensor is a sensor element to connect to electronic circuit with Wi-Fi model. In this case, with this sensor detector, this detector may be used in one vehicles or air vehicles or some other vehicles, because this is a very compact light and also can be remote controlled, and real-time observing by screen the results, real-time observing by screen of mobile, and the sensor response can be recorded by SD card. This is very important because when on the air vehicle it is going to detect something, and some detected, and then it gives opportunity to detect not one place and detect some other places. Of course, it is under controlling, and then the character can be analyzed results after detection procedure. And reusable sensor element. It means that sensor elements can be changed very easily. In the conclusion, I can say that developed bias carbon nanotube-based sensors has possibility of detecting TNT directly in air by vapor pressure, 10-8 atmosphere at room temperature, expected sensitivity around 1 ppb, one the best in the literature. Selectivity not excellent, but much better than metal oxide based sensor. Fast rise time, rapid recovery time. No need of high temperature, such as metal oxide based sensors. It is just in room temperature working. And low consumption, very compact and lightweight sensor device. This work is financial supported by NATO SPS for Peace and Security Program, cooperation with the IMEM Institute, Dr. Claudius Ferrari Research Group, and the University of Parma, Professor Francesco Sanson's group. Thank you very much for attention. So I am ready for the questions.
Thank you, Dr. Nahida, for your presentation. Is anyone having any questions?
Yes, Professor Adnan Abdelghani.
Yeah.
From Tunisia.
Yeah, you can proceed with your questions, Dr. Abdelghani.
Yes, just thanks for Professor Nahida for this nice presentation. I am working in the field of gas sensor and explosive sensor since 10 years, and mainly with the NATO. And I have NATO with the SPS program. And I have just a question. It's about, as you know, that the FLIR company or manufacturing unit in US develop GCMS handle system and EMS handle system for explosive and for neurotoxic gases, which are the best technique in the market. How you think that sensors, what we are developing, because I'm working in gas sensor also since 15 years, but I found that there is a lot of missing things that we neglect, and mainly the norms. When you like to develop a sensor and you buy it or you put it in the market, the provider will ask you for norms. And here, when I say norms, it's mean, for example, the ISO 17025. It's a standard norms for measurement for most of classical technique and normally for sensor. And sensor, gas sensor are for detection or for identification, because there is two things are different. Sensor, what we are developing is only for detection, but for identification, we can do identification with the sensor that we develop.
Yes.
Then my question, how the future is for this sensor, mainly metallic oxide sensor or carbon nanotubes, because I used carbon nanotubes and I work on the decoration of carbon nanotubes with gold nanoparticles, and we functionize them with aminothiols, with carboxylic acid thiols, but still we have a problem of selectivity, of response time, of stability, of humidity effect, and this a lot of problem. Then how do you think that this kind of sensor can be in the market in the future and can replace the classical techniques, which are very expensive but are the best one in the market now, and they are military use?
Yeah, I understand you. Thank you very much for question. Yes, this is the problem. That's therefore in my slides I showed different type of sensors already developed, and not all, even some of part or spectroscopical methods or metal oxides and so on. We know, everybody knows that the metal oxide sensors. They are the problems with the selectivity. Of course, I can say that, but these experiments we did in Italy in the laboratory, but due to pandemic, the last year we could not go to there and share our experiments to do together, but my colleagues did a condition that's of course also tried to use another vapors to detect how is selective. This is just for TNT or others also. Of course, to find TNT, for example, TNT for us is not so easy. We could not found it. Only just my colleagues in Italy, they found something and they did experiments. This is the problem for us to find such explosive materials and make a lot of experiments and to be sure that this is more precise, detect just only TNT or nitroaromatics, for example. But of course, it needs to be improved. Not this is not finished that we did. This is needs many works, many experiments, many ideas that can be improved the results. But just I can say. But in our I don't know if my screen is still is active, but I can say that we are based on the mechanism and that mechanism that I showed you, electron-rich aromatic ring and electron-poor aromatic ring. But we use just this because also I used carboxy. Just one moment. This I want to note. We used for comparing. We used also carboxylate carbon nanotubes. We used also clean nanotubes, but they are not react to these vapors. Just amino group created amino group samples reacted to this vapor.
Yeah, but the functionalization of carbon nanotubes still have problem. Then I don't think that this kind of sensor are stable for 6 months, for example.
Yes, still stable, because I have sample more or less 1 year, but my samples are still can work without problem. Just if in every electrochemical sensors after some time needs to be changed. Yes. Because this is chemical, but carbon nanotubes are more stable material, and if of functionalized groups are covalent, maybe something stable can be. But of course, every sensor can have sometimes active, but you
think that AACVD technique is the best technique for deposition of carbon nanotubes? Because you know that microelectronic industry are using another technique for high volume production.
Yeah.
But AACVD, I use the same technique, and I use the airbrushing also.
Aerosol CVD, you use aerosol CVD? Because is a German, because I used this technique I used first in Dresden, in Germany. They are very Germany solid state research institute. They are very specialized for in this carbon nanotubes deposition, and I learned, I trained in that. Then this machine I bought for my group. Due to the project, and now in my country, in our laboratory we can synthesize carbon nanotubes. They are very long, and they are also good parameters.
By the airfield at Cooper's Cross, and I saw an elderly woman collecting clothes along the perimeter fence.
What? I cannot. The internet connection is not so good. Sorry?
No, it's not me. Just thank you very much, and you can exchange emails together. But think about the Move 360 drone that's served by
Yeah. Yes.
They are a good drone with the 5
Hello?
6
Thank you very much
sensors
for
with
questions.
the
I
camera.
will share with you my yeah. Okay. Your email would be interesting discuss with you separately by email, of course.
Okay, thank you.
Thank you.
Okay. We can
Okay.
change our emails. Thank you very much, organizer.
Yeah. Is anyone having else any questions? Okay, thank you, Professor Nahida, once again for your presentation. So now we will move towards the next presentation. It is from Dr. Rosella Di Marco from University of Udine, Italy. Hello, Dr. Rosella. Are you ready for your presentation?
Yes, I'm ready.
Yeah.
Just a moment. I share my screen.
I'm going to make you the presenter. Okay, it's done. Now you can click on the screen button and share your presentation with us. Yes, now it's visible to all of us. You can start your presentation.
Okay.
Yeah.
Just a moment. Okay. Okay. Thank you, Jessica, and good afternoon, everybody. I would like to present here my research work on self-assembled monolayers of zeolite for a rapid detection of cancer and inflammatory cells. Okay. The artificial materials were applied in biomedical and biotechnological fields. For example, sensors, microdevice, cell culturing, and tissue engineering, where in this case, the material surface was used to increase the cell adhesion by immobilization of integrin antagonists to give integrin antagonists that interact with integrin present on osteoblast cells to give the tissue regeneration. The biomaterials can be synthetic or natural polymers, metals, ceramics, or nanostructured material. I focus my attention on nanostructured material, and I use the self-assembled monolayers because it provides a large surface area and a multiplicity of contact points between cells and the nanomaterials. In particular, I used some of zeolite because the shape can be modulated from long cylinders up to very flat discs. The central core permits the localize to fluorophore with correct sites. The nanoparticles showed cavities oriented in one dimension and perpendicular to the substrate. The regular distance between adjacent channels consents spatial control of the external functionalities. We developed in this project 2 generation devices, and we used 2 different integrin ligands. Alpha V beta 3 that recognize the cancer cells and alpha 4 beta 1 to recognize the immune cells. Integrins are heterodimer protein localized on the extracellular matrix, and they are overexpressed in both cancer and immune cells. They are formed by two subunits, alpha and beta, that interact with the natural ligand fibronectin and vitronectin. This interaction is responsible of the pathway activation inside the cells as survival, proliferation, migration, and angiogenesis. For the preparation of the first device, we used an antagonist of alpha-V-beta-3 integrin, a cyclic pentapeptide, arginine, glycine, aspartic acid, phenylalanine, lysine. And this pentapeptide contain the tripeptide sequence arginine, glycine, aspartic acid, important to recognize alpha-V-beta-3 integrin. We prepared this pentapeptide on solid phase peptide synthesis. We started from chlorotriethyl resin preloaded with glycine. Following the following amino acid have been coupled with HBT, HB2, and DPA in DMF with solvent at 40 watt for 10 minutes. The deprotection steps of protective group SMOC was performed with piperidine 20% in DMF under microwave conditions. We repeat these steps several times for each amino acid, and we obtained the linear pentapeptide, which was cleaved from resin by trifluoroethanol dichloromethane at room temperature for 90 minutes. The final steps was the cyclization of this linear peptide in presence of diphenylphosphorylazide, sodium bicarbonate in high dilution DMF. And in the end, the deprotection of side chain of arginine and lysine to give the final compound. For the preparation of the first device, we divided the synthesis in two steps. In the first step, we used zeolite and we functionalize it with DXP is a dye and ICPTS. In the second steps, the glass surface was functionalized with APTES. The amino group of this reagent was used to form a urea bond with isocyano group of the zeolite. After microprinting, important to obtain order distribution of the zeolite on the glass surface, we introduce a pentapeptide, cyclic pentapeptide, and we used the amino group of lysine to interact with isocyano group present on glass surface to form urea bond. The zeolite was characterized by scanning electron microscopy, and I reported here the images. In the pictures A and B, we can see the zeolite crystal structures before and after DXP functionalization. In the pictures D, C, and D, we can see the structure of the nanoparticle before and after microprinting. On the left, I reported the XPS analysis, where we observed the nitrogen amount is increased. Okay. The device was tested on a cell adhesion assay, and we used HeLa and glioma cancer cells and T293 HILT cells. We visualize cancer cells with DIO and T293 cells with DID. After an incubation time of 30 minutes, we can see at the confocal microscopy that only the SAM with a cyclic pentapeptide showed a large amount of cancer cells, while the HILT cells are not present. In the second device, without ligand, the cancers or HILT cells are not present. I reported here the cell counts. This experiment confirmed that the important to use the integrin ligands, because in this case, this ligand is responsible of the adhesion cells on the glass surface, and is another important information that we obtain from this experiment is this: the nanoparticles zeolite is not involved in the adhesion assay. To test the selectivity of this system, we analyzed these two SAMs on cocktail cells, and we used HeLa and T293 cells and glioma in the presence of HILT cells. In the same condition as before, we observed that only cancer cells, I reported here the confocal microscopy images, only the cancer cells were present on the glass surface. Indeed, in the SAM without integrin ligand, the cancer cells are not present. On the left, the cell counts that confirm these results. In the second generation device, we used an antagonist of alpha-4 beta-1 integrin, or very late antigen 4. Alpha-4 beta-1 is overexpressed on the surface of most mononuclear lymphocytes, includes eosinophils, monocytes, T cells, and it is responsible of the lymphocyte adhesion and migration across the blood endothelial barrier during inflammatory response. In the normal condition, in the normal situation, circulating immune cells in the bloodstream conduct survivals by rolling on the endothelial surface. At this stage, the selectins mediate reversible attraction of circulating cells to the vessel wall by tethering and roll mechanism. Alpha-4 beta-1 integrin present on the leukocyte surface interact with VCM1 and MEDCAM ligands expressed on the endothelium cells lining the blood vessel, and the leukocyte begins adhering along the vessel wall. In proximity of an inflammation, the local release of mediators such as chemokines and cytokines stimulate adjacent endothelial cells to overexpress VCAM1 on their vascular surface. Activation of the lymphocytes by chemoattractive is true to promote a conformational change in the integrins to a higher affinity state, and triggers their clustering along the contact surface, which rapidly strengthens integrin-ligand interaction, leading to form a strong firm adhesion and is to arresting the cells. Was arrested, the immune cells can penetrate into the underlying tissue. If the infection or inflammation is not resolved, the condition becomes chronic. There can be an exaggregate extravasation and lymphocyte can worsen the pathological conditions, resulting in systematic tissue damage. This process is on the basis of pathologies such as allergy, asthma, Crohn's disease. With this research, we would like prepare a rapid and non-invasive diagnostic test to detect the immune cells in biological fluids. In this case, we prepared a second generation device, and we used two different integrin antagonists. In particular, we used the tetrapeptide glutamine isoleucine aspartic acid serine that is a minimal binding sequence of ligand VCAM1. And we used also the semisynthetic peptide bio-1211 and potent alpha-4 beta-1 integrin ligands. We prepared these two peptides on solid phase peptide synthesis in the same condition as before. And in this case, we used a Wang resin. After the preparation of the peptides, we start to prepare the device. And in the same condition, we used the same procedure as the first generation device. And the zeolite was functionalized with DXP and ICP-TS. After that, the amino group of APTS present on glass surface was connected by urea bond to the zeolite to form the first part of the system. And to obtain the final device, we linked the two peptides. And we used the amino group of the tetrapeptide and the amino group of bio-1211 to form urea bond, and the thionyl group of serine to form thiourea. We prepared another SEMS, where in this case we used a terbutylamine. This we use it in the biological assay as negative control. The biological assay was conducted by adhesion experiment with Jurkat and X cells. The Jurkat cells express the integrin alpha-4 beta-1, while the X cells, these integrin are not present. In this case, we reduce the incubation times to 15 minutes, and we observed at confocal microscopy that only the device with bio-1211 as ligand showed a large amount of Jurkat cells, while the first and the second SEMS with the tetrapeptide with the sequence to recognize VCAM1 in the were present in small amount. In the last SEM with butylamine, we can see that the Jurkat cells are not present. In the X cells, we can observe that the cells in this case are not present. I reported here the cell counts of these experiments. In conclusion, we prepared the two generation device. In the first generation, we used a cyclic pentapeptide that contain RGD sequence to recognize the cancer cells, and we observed that this device recognizes the cancer cells in selective manner. In the second generation device, we reduced the time at 50 minutes. We used, in this case, two different ligands to recognize the integrin alpha 4 beta 1 present in immune cells. And we observed in this case that only the sequence bio 1211, an antagonist of alpha 4 beta 1, showed a large amount of Jurkat cells. With the second ligand, we observed the very small amount of cells. In the future, we will prepare a third generation device where this antagonist that we obtained here, important results, the cyclic pentapeptide and bio 1211, are linked on the same nanoparticles. This is my last slide, and thank you for your kind attention.
Yeah, thank you, Dr. Rosella. It was a nice presentation. Is anyone having any questions? Okay, I think there are not. So thank you once again. We will move towards the next presentation.
Bye.
Bye. Have a nice day. Yeah, our next presentation is from Dr. Abdel Ghani Adnani from University of Carthage, Tunisia. Hello, Dr. Abdel Ghani. Are you ready with your presentation?
Yes.
Yeah, okay. So, yes, I have making you the presenter. So now you can share your screen and start your presentation.
I have to look. Oops.
Yes, now it's visible. Yes, yes.
It's visible?
Yes, it's visible.
Yeah, but I have to find the...
No, now it's not visible. Earlier it was visible. Yeah, it's perfect now.
Yeah, but I have to find the presentation. Where is it?
Okay, okay.
Here. Now it's visible?
Yeah, it's visible.
Okay. Thank you very much. My name is Adnan Abdelghani from the National Institute of Applied Science and Technology in Tunisia. My presentation will deal with nanobiomaterials for biosensor development, and I will speak about microtechnology limitation and norms. Here the summary. I will start with the introduction to biosensors, and I will speak about the application of biosensor, and I will give two examples. After I will speak about limitation and norms related to these devices, and I will finish by a conclusion and perspective. As you know, since 15 years now, we speak about sensors development, sensor for food security, sensor for air quality, sensor for medical diagnostic, sensor for military security, and we speak about Internet of Things for intelligent smart city. These sensors are based mainly on microelectronics technology. Also, after the pandemic of COVID, we speak a lot of biosensor because, as you know, classical technique like ELISA, PCR, or GCMS are expensive and now remote sensing. But in the market now, we have this two biosensor. The first one is the glucometer that you can buy it and you can test your concentration of glycemia every day, and it's not very expensive. And you have this surface plasma resonance system developed by Biocore, Sweden company, which is very expensive, but it's very interesting for multi-analyte detection and for biophysical studies. As you know, there is two detection methods, one with fluorescent molecules when we are labeling analytes or bioreceptor, and this is mainly the technique used for spectrophotometry, ELISA technique, and PCR. And this technique, as I say, are expensive, time-consuming. And the idea, we like to develop biosensor based on electrochemical methods, optical methods, mechanical methods, without fluorescent molecules, and we hope that this biosensor can be rapid, sensitive, selective, and not very expensive. What's a biosensor? Just to remind, the biosensor, it's microelectronic devices that convert the interaction between the analyte that we like to detect with a bioreceptor that is fixed on a transducer. This transducer can be electrochemical, optical, conductimetric, piezoelectric. And this interaction, we give electric signal, which can be amplified with the amplification system. And then the last, we have electric signal, and this electric signal can be related to the concentration of the analyte that we like to detect. And here an example of different transducer technique that exists, and you can see a lot of paper in different journal, people using this technique. The same also for bioreceptor, because as I said, we need the bioreceptor. Nanomaterial for biosensor are very large, and people using antibodies to detect antigens, people using DNA to develop DNA biosensor, or aptamers for biosensor detection. And each technique here for aptamers, you can measure the current versus the potential. For antigen antibody, you can use crystal quartz microbalance technique, and for DNA biosensor, you can use another technique also. This bioreceptor or nanobiomaterials, we need to characterize them at micrometer scale and nanometer scale, and we need sometimes atomic force microscopy, transmission electromicroscopy, Raman photoluminescence, scanning tunneling microscopy, and all these techniques are very useful to find at least something published in different journals to have good results. Let's speak about biosensor for bacteria detection, and here the rapid kit test that you can find in different manufacturer, and mainly HTDS or Tetracore company. This kit, it's used for anthrax detection for military use. Then it's for bacteria detection. And when I go back to the bacteria detection, it can have two ways. We can develop immunosensor for bacteria detection when we fix or we immobilize the antibodies with this specific for bacteria. And we can also use, we can also use a phage sensor. It means we use a bacteriophage which is sensitive for one bacteria. And here the two systems will be different, because in the first case, when you have the immunosensors, you will have only one signal, and this signal is the binding signal. But when you use phages, for example, T4 phages to detect E. coli bacteria, K12, you will have two signals. Binding signal, the interaction between the bacteria and the phages immobilized on a solid substrate, and after the second signal, which is the lysis. And we expect to have an impedance increase in the first signal, and after an impedance decrease, if we try to make the measurement with electrochemical impedance spectroscopy. And this is what we do. We use this phages bioreceptor because they are easy to handle, they are a stable bioreceptor, and they are less expensive than monoclonal antibodies. Then phages T4 can be fixed on solid substrate like interdigitated microelectrodes by physisorption technique. After we fix the BSA bovine serum albumin to block the unspecific sites, and after we go with the detection of different concentration of E. coli. Then we fabricate our microelectrodes and digitate microelectrodes in a clean room, and we have different configuration. We have this 180 fingers on silicon, and we have a large and width of 100 by 10 micrometer, and then you can have this system when you can make the electrode contact, and you will use reference and work and counter electrode, or you can use microelectrodes where the reference electrode and work electrode and counter electrode integrated on one chip. Then here the impedance electrochemical measurement that we do in the lab. When you have a cell, when you have the reference electrode, you have the counter electrode, and you have your work electrode here based on interdigitate gold microelectrodes, and we try to test the reproducibility, the phase stability, and we use the physisorption technique, which is very easy and enough for detection of a low concentration of bacteria. Then here the first experiment or results when we study the impedance versus the concentration of different phages, and we can arrive or we can establish a high concentration of phases which allow us to detect E. coli in water interface. For example, here the impedance versus the time for the two curves with two concentration of E. coli using phages, in the left using phages, in the right using antibodies, and we have the curve with a negative test. You can see, for example, for using antibodies, we have this high signal, impedance decrease, and after saturation. And when you don't use the antibodies, you have no signal, that is a negative test. And for phages, you have an increase of the impedance stabilization, and after 30 minutes, you have a decrease, and this decrease is due to the disease. And you can have a negative test using lactobacillus bacteria. Then what we obtain, it's specific to the interaction between T4 phages and E. coli with a concentration of 10.5, I think, coloniform unit per milliliter. And here, the calibration plots, when you have the logarithmic variation of the impedance versus logarithmic E. coli concentration for E. coli and for lactobacillus using phages, and this work has been published in Biosensor and Bioelectronics in 2010. Moreover, we make detection of E. coli in mineral water, and we inoculate mineral water with different concentration of E. coli, and we test this mineral water with two bioreceptor phages and with the antibodies, and you see the high curve of the phages because, as you know, mineral water have concentration of salt, and antibodies normally don't like a lot of salts, and this is why mainly when we are working with antibodies we use PBS buffer, but in a real sample like mineral water, phages are more interesting than antibodies. We go one step further when you have the reference electrode, counter electrode, work electrode integrated in one chip with microtechnology fabrication procedure, and we do a microfluidic cells with our partner, and we integrate these microchips in two compartments for two tests in the same times using electrochemical impedance spectroscopy when you have a low volume of analysis, about 50 microliter. And when we go from 5 milliliter to 50 microliter, the kinetics will be different and everything will be changed because you have a low current, we have a high impedance, and if you see the variation of the impedance for this time, before I show that we have releases after 30 minutes, now we have releases after 100 minutes, more than 1 hour. And we can go to low detection limit because we have low volume for analysis, and we can detect 3 coloniform unit per milliliter of bacteria in low volume. This is the first part of bacteria biosensor And now I go to the second example for biosensor for C-reactive protein. You know that C-reactive protein, it's a biomarker. It's a biomarker for inflammation, and high concentration of CRP can cause high inflammation, high accident, or high problem like cardiac crisis or cerebral vascular accident or other problem. Then the idea is to detect the C-reactive protein using antibodies and to try to find a very rapid solution. And to develop this, we use a thin layer of protein G before making the immobilization of the antibodies, because using protein G thin layer will give a higher sensitivity, a higher orientation of the specific sites of the antibodies. And here I show the Nyquist plot of the impedance versus the concentration without using protein G, and the second one with protein G. And you can see in the calibration curve that using protein G enhance sensitivity, and we can go to very low concentration for CRP detection. We go another step is to use our system for real sample, and we do measurement with Bichat Hospital in Paris. We take from human plasma of patients they have a high concentration of C-reactive protein. We make dilution and we measure the variation of the resistance versus the concentration, and you can see that for the three sample of human plasma of a patient, we can detect and we can say that this patient have a high concentration and can have a problem after. This is the electrochemical methods, and we use the commercialized surface plasma resonance. It's a GWC system where we do the same measurement, and we like to what we obtain with electrochemical measurement, we confirm it with electric measurement. And here I show the variation of the surface plasma resonance intensity versus time for different concentration of CRP injection with the protein G and without protein G. And we, as you can see, that protein G give also the good concentration, and we do also real sample measurement from human plasma of 3%. And here the summary of the result. All these results are very interesting, and you can see electrochemical methods and optical methods can give the best results. You can reproduce the results. You can regenerate with some difficulties the surface, but in the same time you still have to go with other steps. Then our idea, what we develop, is the multi-array system, and we like to make a very small platform when you have 10 microfluidic cells and with different microchips. Each microchips have a control electrode, a reference electrode, and a bioreceptor, and you can enhance the sensitivity by using magnetic nanoparticles, and you can make all the readout with the STM32 card, and you can have a small platform which can be read with the sample readout. Here the system that has been developed recently, and you can say you know that Palm Science, Drop Science, Metron are fabricating this kind of micro electrodes on alumina, but on silicon it's more comfortable as it's less expensive, and they are using voltammetry cyclic curves or calibration or impedance or resistance measurement, but still have other difficulty to enhance. Then, as I said, CMOS technology is still the best technology. It's a low-cost technology, and microelectronics technology has made a lot of effort for development of transistor, for the development of microprocessors, and I think we still stay on silicon technology. It's the less expensive, low-cost technology. The limitation we can find also in microelectrode fabrication, as I show the width and the length of interdigitated gold microelectrodes is very sensitive. When we go to low dimension, you have high current and you have high noise, and here you have a lot of problem. Another problem also is integration difficulties in one package, what we call unbanded microsystem with microfluidics. It's mean microelectrodes arrays with microfluidic cells. When you have everything automatically can be run out. Moreover, transduction technique cannot be miniaturized more, and electrochemical techniques are good, optical also, but we have a problem of miniaturization. As I say, we have a lot of signal drift, underwater interference, and a lot of interference in complex medium when we like to detect bacteria or you like to detect another analyte which can interfere with others. Nano biomaterial for biosensor application, most of them are unstable for industrial use. You know that a company or an industrial like to have low cost system, with a good fiability, with a good reproducibility, and which is very, very cheap. We have also pH and humidity effect for most of nanobiomaterials that we use. Regeneration of this nanobiomaterials or of the surface, it has also difficulties, and the drift of signal versus noise, it's a big problem, and the functionalization is a very long procedure. This is why in our work we use physisorption technique, which is very easy technique without using self-assembled monoray technique or other leakage technique, which can make things complicated. Now, detection and identification needs norms, and detection and identification are complementary issue. We need two complementary techniques with reference. You know that, for example, for Raman, handle Raman and handle FTR, these two techniques are for identification and not for detection. And we have a database from the provider, and we have a database from a National Institute of Standard and Technology. And we have to think about doing something like this in development of biosensor, because biosensor or in general sensor need a reference to calibrate it or to compare it, like a pH meter, which is a sensor, but you need pH 4, pH 7, pH 10 to make the calibration. For sensor and biosensor, as we are doing measurement, we need to follow the ISO 17025 norms. We need also biosensor reference data, what we call in French étalon, and I think in English stallion. Industrial need fiability, efficiency, and low cost. And here the standards and regulation of nanotechnology, and this Euro Nano Forum 2021 that I take part, and there is a lot of efforts to do to develop biosensor and gas sensor with norms and with all the characteristics that I mentioned. Here recent studies, this is why I forget. Then perspective, we have to work on biocompatible flexible microelectrodes, the low cost. We have to think to work on integrated biosensor arrays, wearable diagnostic biosensor. We have to work on integration of biosensor array system with another reference methods like RT-PCR. Then you have detection and identification. We have to establish a NIST reference data for biosensor and even for gas sensor and for ion sensors. And we have to think to use another nanobiomaterials for in vivo application. You know that silver colloid graphene have a problem of toxicity, and we can't use them for in vivo. Then another big work is to develop reference or stallion for biosensor and to follow the standard and the regulation in the world. And here the recent study that I see it by many people, they publish wearable technology where you can use different nanobiomaterials or other materials which are not toxic and can be used with the flexible wearable sensor technology. Then, as I say, there is a lot of work to do, but we have to be careful because companies need something reliable, fiable, and very cheap. Here my group in Tunisia. Then I have thanked the NATO SPS program, the DID, the German academic Foundation, the National Science Foundation, the Alexander von Humboldt Foundation, the European Campus for the financement of the different projects. Thank you very much.
Thank you,
Hello?
Dr. Abdul Ghani. Yeah, hello.
It was okay?
Yeah, it was okay. It was a good presentation. Is anyone having any doubts? Oh, sorry, any questions? Okay, I think there are no questions. Thank you once again, Dr. Abdul Ghani.
Thank you.
Yeah, so now we can proceed towards the next presentation, and it is from Dr. Alessandro Vigiani from Italy. Hello, Dr. Alessandro.
Hello?
Are you ready with your presentation?
Yes.
Yes. I'm going to make you the presenter.
Okay. You have
Yeah,
to give me
it's
the
done.
permission. Okay, perfect.
Yes, it's done. Now you can click on the screen button. Yes, now it's visible. You can start your presentation. Yes, perfect.
Okay. I have a. Okay. Okay. Good afternoon. I'm Alessandro Beduini, a PhD student of industrial chemistry of the University of Milan. And today I will talk about my master thesis work and a work that I'm carrying on also in this is my first year of PhD. The title is Copolymeric polyamido amines as flame retardants for cotton. Today I will talk about the importance of studying flame retardants for polymeric materials and their state of art. Then I will talk about the aims of my work, the synthesis and the characterization of polyamido amines. Polyamido amines are biocompatible and degradable polymers synthesized by the azamical polyaddition of primary amines or secondary diamines to bisacrylamines. Then I show you the characterization of polyamido amines cotton fabrics and their application. Characterization with thermogrammetric analysis and TGA coupled with IR spectroscopy, combustion test, in particular vertical flame spread test and horizontal flame spread test, and morphological characterizations of cotton fabrics and their residues. At the end, the conclusion and the future perspectives. First of all, I want to show you some frameworks of a video made by National Institute of Standard and Technology. They simulated electrical fire of a Christmas tree in a domestic scenario. And we can observe that only after 30 seconds, we are in a situation called flashover, during which it's impossible to see a get out. In my lab, some studies about polyamido amines as flame retardants were done, in particular about linear polyamido amines and disulfide-based polyamido amines. The first one, linear polyamido amines, were found to be intumescent. So these polymers, when they are exposed to it, start to form a carbonaceous structure called char. This char starts to swell in order to cover and protect the substrate below. reducing the passage of oxygen and heat. In this case, the temperature on cotton surface will be less than the temperature on the char. In the second work, the sulfate polyamidoamines were found to be intumescent, but also radical scavenger. So these type of polymers are able to capture radicals present in the environment, blocking also the self-sustained combustion. In my work, I studied the combination of different monomers, synthesizing copolymers based on polyamidoamines, so biocompatible and degradable polymers, in order to obtain a synergy between the intumescent feature of linear polyamidoamines, so the first type of polyamidoamines, and the feature of disulfate polyamidoamines that act as a radical scavenger. Then I tested the flame retardant ability of copolymers, comparing also their performances with the performances of the homopolymers. I synthesized some copolymers, and today I want to show you one of them, that is the glycine and cysteine based copolymer. It was synthesized starting from NN-methylene bisacrylamide, cysteine and glycine with a Michael type polyaddition using water as solvent at room temperature for 2 days. At the end of the reaction, no side products are present and no purification is needed. I synthesized the homopolymers M-glycine and M-cysteine, and the copolymers with a different ratio between glycine and cysteine. I characterized these polyamidoamines with FTR, ATR, with HNMR, and with thermogravimetric analysis, TGA. And then I applied these copolymers on cotton fabrics. First of all, I heated cotton at 100 degrees for 3 minutes in order to remove the absorbed moisture. Then I deposited polyamidoamines water solution on cotton fabrics. I dried at 100 degrees for 3 minutes, and I weighted the sample, calculating also the add-on. The add-on is defined as the weight of polymers present on cotton surface after treatments. These coatings are not durable. In fact, they could be washed away after a few washing cycles. But now we are working with copolymers and homopolymers in order to graft polymers on cotton fabrics, and we are obtaining good results. I applied on cotton fabrics add-on of 16% for all copolymers. These add-ons are comparable with the add-ons used in the commercial flame retardants nowadays. Then I characterized the cotton fabrics with chemical and morphological characterizations, with thermal analysis, with combustion tests, and morphological analysis of combustion residues. Today, I will show you only some of them. We can start with the scanning electron microscope. With this technique, we can observe that untreated cotton, on untreated cotton, we have the fibers are rough. Instead, for what regards cotton treated with copolymer, we have an homogeneous coating that cover all the cotton surface. Then I perform thermogravimetric analysis of untreated cotton, cotton treated with homopolymers, and cotton treated with copolymers, and in nitrogen and in air. In all graphs, we can observe that up to 350 degrees, untreated cotton seems to be more stable. So what happens at 350 degrees? In order to understand this, I did a muffle treatment simulating the TGA analysis using the same parameters, but increasing the weight of copolymer used. In fact, in TGA analysis, I used 5 milligrams of copolymer. Instead, here I used 1 grams of copolymer. After 350 degrees, we obtain this intumescent behavior of polyamidoamines that cover the cotton surface, reducing the oxygen and heat transfer. And for this reason, the cotton treated with homopolymers and copolymers are more stable from 350 degrees to 80 degrees. Then I studied the emissions of untreated cotton and cotton treated with homopolymers and copolymer using a TGA analysis coupled with IR spectroscopy. I observed the presence of signals of stretching of carbon dioxide, of carbon monoxide, of species with carbonyl groups, that these species are the most dangerous because they are combustible, and also the bending of carbon dioxide. I observed the same peak in different absorbances for what regards the cotton treated with N-glycine. Also for cotton treated with homopolymer M16. And also for cotton treated with copolymer. I want to highlight also that there is no presence of sulfur dioxide and sulfur trioxide emissions. Then I compared the emissions of CO2 of untreated cotton, the black line, with cotton treated with M-glycine homopolymer, the green line, the cotton treated with homopolymer M16, the blue line, and the cotton treated with copolymer, the red line. For the last two, we can observe that the first peak is presence less emissions of CO2, and the second peak disappeared. For what regards cotton treated with M-glycine, we have similar results for the first peak, and the second peak is higher than untreated cotton. For what regards carbon monoxide emissions, we have the similar result of carbon dioxide. So for cotton treated with M16 and cotton treated with copolymer, we have a reduction of first peak and the disappearance of the second peak. Instead, for M-glycine treatment, we have a similar result of untreated cotton. For species with carbonyl groups, we have a reduction of the peaks for both of three treatments. Then I performed a combustion test in order to test the resistance to a flame and the resistance to an irradiative heat flux. Today we show you the resistance to flame test, in particular the vertical flame spread test, where the flame remains in contact with the sample for 2 seconds. The flame is a methane flame, and this test is more drastic than the horizontal one. The horizontal flame spread test instead is a test where the flame remains in contact with the cotton surface for 3 seconds, with the same flame of methane flame of the vertical test. Okay. In this slide, we can observe the untreated cotton after vertical flame spread test. Untreated cotton burns quickly, leaving minus than 2% of the residue after only 31 seconds. Using a treatment with copolymer with 30% of cysteine and 70% of glycine, we can observe an increase of residue, 31%, and if we increase also the contents of cysteine, we increase also the percentage of residue, 41%. Using a treatment with copolymer, 50% of glycine and 50% of cysteine, we obtain these excellent results because the flame is not present on cotton surface only after glow phenomenon, and after at the end of the test we have a residue of 95%. Similar result, we obtain similar result with a treatment with the highest with the copolymers with the highest contents of cysteine. But for economical reason, it's better to use the copolymer with 50% of glycine and 50% of cysteine. Then I studied the morphological characterization of cotton treated with copolymer using a scanning electron microscope with 3 different magnifications. We can observe the intumescent behavior of our polyamidoamines that start to swell in order to cover the fibers below. I performed also horizontal flame spread test with all copolymers, and we can observe that all copolymers treatments extinguish the flame, and we obtain a residue from 82% to 94%. For this reason, I tried to find the minimum add-on of treatment with copolymer, 50% of glycine and 50% of cysteine, and we observed that with an add-on of 7%, we obtained a residue of 72%, and we are able to extinguish the flame. Instead, with an add-on of 5%, we are not able to extinguish the flame, but we obtain a residue of 32%. So the minimum add-on is 7%. Then I did an ADX analysis of residues of cotton treated with copolymer in order to understand which elements are present on cotton surface. We can observe the presence of carbon element, the presence of oxygen element, but the most important is the presence of sulfur. So the sulfur that is present in cysteine molecule is on the condensate phase, so on the cotton surface, and not in the gas phase. So in the state of art, we can observe that the M-glycine treatment extinguish the flame only in horizontal configuration with an add-on of 5%. M16 treatment instead extinguish the flame in vertical configuration with an add-on of 16%, but in horizontal only 12%. For instead using copolymer treatment, we are able to extinguish the flame in horizontal configuration with an add-on of 7%, and in vertical with an add-on of 16%. In conclusion, for the first time, polyamidoamines copolymers were found to be excellent flame retardants for cotton fabrics. These copolymers work better than M-glycine homopolymer in vertical configuration, and also than M16 homopolymer in horizontal configuration. The emission of carbon dioxide, carbon monoxide, and species containing carbonyl groups were reduced using a copolymer treatment, and there is no presence of sulfur dioxide and sulfur trioxide emissions in the gas phase. Now we are working in order to graft homopolymers and copolymers on cotton fabrics in order to obtain a durable flame retardant coatings. And we will test the copolymer on different cotton grammage or different type of textile. And we want to test also homo and copolymers on polyurethane foams. We start with this preliminary study, and we can observe that untreated polyurethane burns quickly, leaving no residue at the end of the test. And with this material, we have also dripping problems. That is a phenomenon that is very, very dangerous. Using a treatment with homopolymer M16, we are able to extinguish the flame, obtaining these results. This is a preliminary result, but is a good start for a study. I want to thank my supervisor genealogy, Professoressa Elisabetta Ranucci and Professor Paolo Ferruti, all my lab mates of my master thesis, and I want to thank also my lab mates of this first year of my PhD, and thank you for your attention.
Thank you, Dr. Alessandro. This was a nice presentation. Is anyone having any questions? Okay, I think there are no questions. Thank you once again for your presentation. So we will move towards the next presentation. We request Dr. Zacharias to present his presentation, as Dr. Vijay and Zuana had requested to postpone his presentation. Hello, Dr. Zacharias.
Hello, Jessica. Hello, everyone. Do you hear me?
Yes. Can you give your presentation now?
Yeah, sure.
Okay, so I'm going to make you the presenter.
Perfect.
Yes, it's done. Now you can click on the screen button and share your screen and start your presentation. Yes, it's visible now.
Okay, perfect. Just give me a couple of seconds to modify some things.
Okay.
That's all. Is it okay?
Yeah.
I mean, is it visible? Okay.
Yes,
okay.
it's
so,
visible.
Good afternoon, everyone. My name is Zacharias Biskadurakis, and today I would like to present you our latest work regarding the thermoelectric performance concerning of bismuth antimony telluride ABS composites. This work has been performed in photonic, phononic, and metamaterial laboratory, which is part of the Institute of Electronic Structure and Laser in the Foundation for Research and Technology in Greece. So, brief information regarding our institute. The institute is located in Heraklion, Crete. Crete is the largest island of Greece at the south part of Europe. Now, this work is a result of a collaboration between people from Crete, ISL 4th, and people of the University of Cyprus in Nicosia. Now, apart from me, 3 other people from ISL 4th and the University of Crete have been involved. These people are Mrs. Argyridri Rimskianaki, a bachelor student from physics department in the local university, Dr. Vasilis Papadakis, a research fellow of the Institute of Electronic Structure, and Dr. George Kenanakis, who is a researcher in the Institute of Electronic Structure and Laser. Now, from in the Cyprus part, we have Mrs. Ioanna Ioannou, who is a PhD candidate in the Mechanical and Manufacturing Engineering Department of the University of Cyprus, along with Professor Theodora Kirachi, who is the chair of the department. Now, a brief introduction regarding thermoelectric materials. Thermoelectric materials are materials which convert waste heat to electrical power through the Seebeck coefficient effect. Here, let me show, excuse me. Okay. Here you can see a thermoelectric power generator device, which consists of 2 thermoelectric legs, which are connected in series electrically. However, they are connected in parallel thermally. So if we hit the upper side of this device, then electrons and holes move towards the colder side of the device, and in this way a thermal current and electrical current actually is produced. Now, the efficiency of such a device depends on the efficiency of the thermoelectric materials used, and this efficiency can be determined through this thermoelectric figure of merit, ZT, where S equals to Seebeck coefficient, Rho equals to resistivity, kappa equals to thermal conductivity, and tau is the absolute temperature. Now, especially for thermoelectric generators, there is the thermoelectric power factor, which gives actually an estimation of the capability of the thermoelectric generator to produce electrical power. Now, in any case, it could be easy to say that if we reduce resistivity and thermal conductivity and increase Seebeck coefficient, then we have the perfect thermoelectric material. However, it's not that easy, since these three parameters, Seebeck coefficient, resistivity, and thermal conductivity, are interconnected through the carrier concentration here. So that's the main, let's say, drawback for realizing efficient thermoelectric materials. Can I ask something? Jessica, do you hear me? Hello? Hello? Is anyone here? Does anyone hear me?
We can hear you.
Okay. Which monitor do you see? The black one or the white one?
Can you repeat the question? I didn't hear properly.
Yeah, I have two monitors, a black one and the white one. Do you see the white one or the black one?
The black one.
The black one. So that's not good, actually. Anyway, okay, let's continue. Now, up to now, the state-of-the-art thermoelectric materials are mainly inorganic materials, and which exhibit very high ZT values, as high as I mean, the ZT values are beyond the unity, which is actually the threshold for real-time, real-life thermoelectric applications. However, they also have severe disadvantages, such as many of them are toxic. Many of them are produced through very complex production processes. They also, I mean, they are also quite expensive to be produced, and they do not show good mechanical properties. In this context, thermoelectric polymers seems to be a very good alternative, since they are low cost and flexible. In this table here, we can see a state-of-the-art polymer-based thermoelectric in comparison with an inorganic thermoelectric material, and we see that they show comparable thermoelectric performance. However, the polymer thermoelectric material is much cheaper. However, even in this case, in order to produce thermoelectric polymers, we need to use very complex chemical routes, and this is the main disadvantage of the polymer thermoelectrics. Now, considering all the above, we propose here another alternative. We propose to mix a polymer material with a state-of-the-art thermoelectric material in order to produce a polymer-based thermoelectric composite. The mechanical mixing seems to be an easy process, with a very short time of procedure, a low cost, and actually it is an industry scale method. Now, in our case, we choose the ABS polymer as the polymer of this case study, and as a thermoelectric material, we choose the bismuth antimony telluride thermoelectric. First of all, we started to synthesize the bismuth antimony telluride powders. I will not go into details regarding the synthesis methods. We use two methods, melting procedure and ball milling procedure. Our collaborators in Cyprus have a long experience regarding this kind of synthesis, and they provided us with a series of such kind of powders as listed in this table. And then we proceeded with the production of the bismuth antimony telluride ABS composites. Actually, we took specific amounts of the thermoelectric material in the polymer. We put it on a vial. The vial is attached on a rotator. The rotator is tilted with respect to the vertical axis, so as to ensure that the two powders will be mixed. The rotation speed has been kept as low as possible in order to avoid heating during rotation, and we let it go for 2 hours. Then we took a small amount of this powder, we put it between 2 PTFE slabs, we press it at 200 Celsius degrees for 3 minutes, and the final result is shown in this picture, which is a foil-like sample with a thickness of 200 micrometers. Now, in this way, we made 2 different sample series. In the first sample series, we kept the mass ratio between bismuth antimony telluride and ABS constant, 80/20. And in this series, in this sample series, the bismuth loading has been changed. On the other sample series, we kept the bismuth loading constant, while we changed the mass ratio between the components. Now, after we produced the foils, we characterized them using various techniques. Here we see X-ray diffraction spectra, typical X-ray diffraction spectra of those films. We see that all of these peaks can be indexed to the bismuth antimony telluride phase. No secondary phases can be observed, at least within the resolution of the instrument. And we see that if we compare samples with different bismuth doping, either we compare samples with different mass ratio, we didn't see any difference between those spectra. So mechanical mixing and hot pressing actually does not affect the bismuth antimony telluride crystal structure. After that, we go with Raman spectroscopy. I will not go into detail to this experiment. However, what we can say that all these peaks observed in this spectra can be identified as peaks corresponding to vibrations between among bismuth antimony and tellurium atoms in the bismuth antimony telluride structure. Now, regarding the morphology of those foils, there are several interesting things that we can show here. So this is a typical scanning electron microscopy micrograph from those produced foils. We see that there are large and small grain clusters, and in some cases, just like here, let's say, we can see that the bismuth antimony telluride clusters are encapsulated into the ABS material. Moreover, we can see that there is a lot of empty space between clusters, which is suggestive for highly porosity. And from EDX spectra, we can see that all peaks observed correspond to elements of bismuth antimony, tellurium, carbon and oxygen for ABS. Now, in direct comparison with pure BST powder, we see that the bismuth antimony telluride powder contains small grains. It is also highly porous, and from this comparison, we can say that the existence of large grains is probably attributed to the foil production process. and it's also it could be also said that the bismuth antimony telluride is not affected by foil production process. Now we go on with the transport properties of those foils. Here we see the resistivity as a function of temperature with respect to the bismuth loading, as well as with respect to the mass ratio. In all cases, we see that the resistivity increases with temperature, and we also see that resistivity decreases with increasing bismuth doping. On the other hand, we see that resistivity decreases with increasing mass ratio. Furthermore, there is an anomaly observed at around 110 Celsius degrees, which is probably associated with the glass transition of the ABS. Now, comparing these resistivity values with other values reported in the literature, and which correspond to other polymer composites containing bismuth telluride compounds, we can say that our samples are quite resistive. They exhibit very high resistivity. And this high resistivity is possibly attributed to the large porosity observed in the scanning electron micrographs, as well as on the small bismuth antimony telluride grain size. Furthermore, in these two panels, we see the Seebeck coefficient as a function of temperature for different bismuth doping foils, as well as for foils with different mass ratio. In all cases, we can see that the Seebeck coefficient values are quite high. Furthermore, the Seebeck coefficient decreases with increasing bismuth doping, and also it increases with increasing mass ratio. Now, in comparison with other polymer composites, which include bismuth telluride compounds, we can see that our samples exhibit quite high S values, which is directly compared to the Seebeck coefficient value of pure bismuth antimony telluride. And this is also possibly related to the microstructure. However, further investigation is needed to prove that. As a result, the power factor of the produced foils is shown in those two panels with respect to the temperature. We see that the power factor increases with increasing bismuth doping, while it is also increases with increasing mass ratio. Now, comparing to other power factors for other polymer composites, we can see that the obtained power factor values are quite close and quite comparable to the other ones, suggesting that our foil exhibits very good thermoelectric performance. And this is attributed, this is mainly attributed to the high Seebeck coefficient values observed previously. Now, in summarizing, we succeeded to produce bismuth antimony telluride ABS composites employing mechanical mixing and hot pressing technique. Actually, this kind of composites will be potentially used in thermoelectric applications. And we found out that the resistivity of those composites is quite high. However, their Seebeck coefficient is also considerably high, and therefore their thermoelectric performance is rather good. Now, if anyone wants to further investigate these kind of materials, he should focus more to improve the thermoelectric performance by reducing the resistivity, as well as he should focus to reduce the bismuth antimony telluride mass ratio without reducing the thermoelectric performance of those composites. Anyway, mechanical mixing and hot pressing seems to be a very promising way to produce polymer-based thermoelectric composites in a short time and in a very low cost. Finally, I would like to say that this work has been already published a couple of months ago. The whole project has been funded from European Union in combination with Greek national funds. And with this information, I would like to thank you for your attention.
Thank you, Dr. Zacharias. It was a good presentation. Is anyone having any doubts? Any questions? Okay, thank you once again, Dr. Zacharias. I think there are no questions from anyone.
Thank you.
So, thank you. So, we can move towards the next presentation. And it is from Dr. Asia Janeki from Abu Bakr Belkayad University, Algeria. Hello, Dr. Asia Janeki. Are you ready with your presentation? Hello, Dr. Asia. Hello, Dr. Asia Janeki. Are you ready with your presentation? As per your request, we have rescheduled your talk now. Okay, I think she is not active now.
Hello,
So,
sorry.
yeah, okay. Hello, Dr. Asia Janeki. As per your request, we have rescheduled your oral presentation in the place of Dr. Mehta. As he is not able to join us today, he will join us by tomorrow. So, are you ready with your oral presentation?
Yes, I'm ready. Wait just a second.
Okay, so I'm going to make you the presenter now.
Yes.
Okay, now you can click on the screen button and share your presentation with us.
Okay, 1 second. It's okay?
Yeah, it's visible. You can start your presentation.
Hello, everybody. My name is Zelaki Asia. I'm a PhD student in the University of Tlemcen in Algeria. I hope all of you are in good health. In this study, we will see the effects of annealing and rheological properties on the rheological and thermal stability of polyacid lactic film. The massive use of plastic began in the 1960s and has grown steadily since. Today, more than 3,000 million tons are projected annually. It continues to grow, especially in developing countries. Plastic owes its popularity not only to its low cost of production, but also to its many practical characteristics, like lightness, resistance to acid, and malleability. In addition, the latter properties stimulate technology innovation, and especially in medicine, building construction, aeronautic, and the automotive industry, which ensure great conform in certain sectors they present is essential. But the massive consumption of plastic causes many problems. Much of the plastic ends in the garbage, and plain plastic continue to contaminate the environment for decades, even centuries. Already today, mountains of plastic are building up in our nature. In addition to better waste management on a global scale, the use of non-biodegradable plastic should be abolished, and a transition must be made. The biodegradable plastic is plastic which degrades under biological action. Some biodegradable plastics are compostable, and many bio-based plastic can be also biodegradable. like polyacid lactate, and this is the polymer that we are going to study. The PLA has been able to replace the conventional petroleum-based thermoplastic thanks to the excellent combination of properties and its process. It's one of the most promising biopolymer used today and has a large number of applications such as healthcare, medicine industry, packaging, automotive application, etc. As comparing to other biopolymer, the PLA exhibits several benefits such as it's eco-friendly, that means that it is renewable sources and biodegradable. It's biocompatibility, that means that it's not toxic, and the processability, it has a better thermal processability comparing to another polymer like PHA, PEG, or PCl. The polyacid lactate breaks down into non-toxic products during degradation, and being biodegradable and biocompatible reduces the amount of plastic weight. The PLA can also be degraded in compost where it is hydrolyzed into small molecules like oligomer, dimer, or monomer. At the temperature varying from 50 to 60 degrees Celsius for 45 to 60 days. The small molecules are then degraded into CO2 and the water by microorganisms remaining in the compost. But like every material, it has its limits, which is low heat resistance, sensitivity to humidity, and the low mechanical resistance. But several solutions and methods of development have been put in place to push its limits, like mix it with another polymer like PBS or chitosan, addition of a nucleing agent like talc or a plasticizer like PEG, the elaboration of composites based on alpha, clay, or cellulose fiber, or mechanical and treatments, which will be the center of our study. To prepare our film, the previously dried pellet of polyacid lactate melted at 200 degrees Celsius in a vacuum oven, pressed, then quenched in cold water, and annealed at 90, 80, 100, and 110 degrees Celsius for 24 hours. As we can see, the first effects of annealing here, the film becomes opaque white. The study was followed by rheometer DRH2 for rheological study and the modulate DSC Q2000 for the thermal one. In this thermogram, we can see a difference between sample in the melted zone. The appearance of double peak in low temperature show two sides of crystal, the small and the big one. But in high temperature, we have just one peak, translated by the presence of one size of crystal, which will increase the crystallinity. Work reports in the literature on the effects of annealing time and temperature of the crystallinity of polyacid lactate has shown that the PLA film of the same structure, having undergone the same thermal history, then the same elaboration, see their crystallinity increase with annealing temperature. Our results are in good agreement with those reports by this author. Indeed, the rate of crystallinity grows from 90% for 80 degrees Celsius of annealing to 25% for 110 degrees Celsius. The mental rheology of polymeric materials reflects the relationship between molecular structure and dynamic properties. Among these properties, the viscosity and elasticity of the molten polymer are important for shaping of plastic. The figures show a strain sweep of 0.1 to 100% at a frequency of 10 radian per second and the temperature of 150 degrees Celsius for the various samples. The DVEL spans about 30% of the chain. Beyond this value, one enters the field of non-linearity in which the elastic modulus are not longer independent of the chain. Please to be sure that we are in the linear domain. The value of 5% was then chosen for all the systems studied. The thermal stability of the different sample was determined for a strain of 5% and the melt temperature of 180 degrees Celsius over a period of 2 hours. As shown in the figure, the PLA film annealed at 90 degrees Celsius for 24 hours show a good stability. We can explain this effect with the small degradation of film in high temperature and the low crystallinity at 80 degrees Celsius. First, we observe the evolution of dynamic modulus and the complex viscosity as function of the frequency at different temperature for PLA film. The complex viscosity presents for all the sample a Newtonian plateau toward low frequency and the rheofluidifiant behavior for high frequency. The points of the intersection of storage modulus and loss modulus remain constant for all the sample. We can conclude that the results obtained by DSC showed an evolution of the crystallinity rate for the annealed PLA films. The degree of crystallinity gradually increased with temperature of annealing, and the better crystallinity is observed for the PLA film annealed at 110 degrees Celsius. For the rheological study in the molten state, it's possible to follow the evolution of viscoelastic quantities at low frequency for the various PLA film. The annealed films show good linearity of the loss and storage modulus and the Newtonian behavior toward the lowest frequency. The different annealing temperature had no effects on the rheological properties, but we observe an improvement of the thermal stability thanks to the crystallinity effects. For the continuation, we hope to study another temperature of annealing and the mechanical properties of the polyacid lactic. Thank you for your attention. If you have any question, you can ask me.
Thank you, Dr. Shazanaki, for your presentation. Is anyone having any questions? Okay, I think there are not. Thank you once again for your presentation. Yes. So moving on to the next presentation, it is from Dr. Mohammad Shanghez from Asia Kia University, Oman. Hello, Dr. Mohammad.
Hi.
Yeah, how are you?
I'm very fine.
Okay, so are you ready with your presentation?
Yeah, I'm ready for that.
I'm going to make you the presenter right now. Okay, yeah, it's done. Now you can click on the screen button. Yes. Now you can share your screen with us.
Yeah, it is okay now?
Yes, it's visible now. You can start your presentation.
This is Dr. Mohammad Shanghez. I'm working at Al-Sarkia University, Ibra, Oman. Today I'm going to present how to get the sub-nano ordering in a polymer system. As we are aware that self-assembly is the well-known process to observe the different kind of self-assembly at nanometer scale. Overall, it determine on the molecular formula of the chemical, especially if we use the polymeric system, block copolymer or homopolymer. Ordering in the system based on the molecular interaction, mostly non-covalent interaction. And as the molecular order improve, they facilitate that carrier transfer either through the overlapping or hooping of the carrier. But there are the limitations. To get the order at the molecular level, it is very challenging. Also, in polymeric system, chains are randomly sometimes organized, and sometimes both amorphous or crystalline region coexist to the various degree. Our work, basically, our objective for the research was formation of sub-nano order in polymer system one-step cost-effective process. Generally, as a chemist, we are aware that cross-linking is a random generated random structure, but nothing in the nature. If we learn from the nature, we go through the observation at nanoscale, and we observe that all these things in the nature is ordered and built up by ordering the molecules at nanoscale level. It means there is nothing in the nature which go in a random way. However, we make, say, determine time. Maybe time is high, or sometimes we are not able to observe. But overall, the reaction, all these things is in a controlled way. So that's why we design, we think, hypothesize that if we cross-link the polymer by controlled way, it can generate. For that purpose, we start the experiments. We take the poly-2-vinyl pyridine as a model chemical purchased from the sigma and cross-link with the 1,4-dibromobutane at 45 degrees centigrade, 48 hours. And we observe that this polymer, this reaction at control, it generate the molecular order in a polymeric system. And we analyze this by XPS, and we observe that nitrogen of the poly-2-vinyl pyridine get quaternized, and it gives the electron board more than 400 that indicate that nitrogen has positive charge. And then we make a block copolymer of this. You can see here that block copolymer with the PHIC, polyhexyl isocyanate, make a micelle and cross-link that. You can see here is a crystalline micelle. We observe that. And we characterize this by the IR Raman spectroscopy, and we observed all the characteristic peak. And they also characterized by XRD, and we get similar peak related to this the lattice. And then we say that how the molecular weight of this polymer affecting that. In this case, we take a very small molecular weight polymer here. Then we shifted to the high molecular weight polymer. And then again, same the reaction, we do that. We can see at lower scale here. And we have a lot of crystal structure, and then same type of ordering we observe here, and like a jeep. And we analyze the application near IR here, near IR and mid-infrared. You see this here, it looks like this. And we observe the plasma band here in the cross-link. Parallel and perpendicular, both are same. And we measure the IV curve with Hall effect, Hall instrument measurement. We observe here Hall coefficient positive and carrier density very high. And from this plasma band, using the Drude model, and we calculate the plasma frequency, then also the same. And conductivity, actually, we reported here in a publication, and very high. And then same method we apply to use this with another method by hydrogen bonding. We again take the poly, this time we take poly-2-vinyl pyridine along with the poly-4-vinyl pyridine, and here the ferrocene dicarboxylic acid. And cross-link, simple in room temperature, you can see that 40-hour change and characterize. They give the order structure like this. And we analyze with the high voltage electron microscope, at sub-nano level, you can see the 1 and 1 nanometer is a real picture. And then correlate with the XRD analysis. And then we analyze with different zone axes. If we see here with big picture, we have see here all this zone and a very nice structure at sub-nano level observed. And after that, we analyze the sample with the electron absorption spectroscopy and then discrete magnetic property. We observe here L3, L2 ratio very high in this FDA system. And the magnetic property increased drastically, almost 100 times high. And it is behave start like that single molecule magnet. And this work get published in Applied Polymer Science with the cover piece. And previous work was published in Advanced Material. Then we try this method to use with the PANI EB and use here the coordination bonding for cross-linking in one-step process. We just make this by this and with the zinc nitrate hexahydrate, this put here in the substrate is spin coated and do the reaction solvent vapor thermal annealing start. And we analyze the XRD here. With that time, you can see the peak is improving, a new peak here generated. And then we again XPS analysis and characterize. And then this measure the conductivity of this. This again becomes very high, it's a 40 times higher than the reported conductivity of PANI EB. Then another may other say, why we take the polymer? Why not we start the monomer from the monomer? And we start from the monomer and put the graphene oxide here as on the reaction. We put this graphene oxide monomer here in situ polymerization, and we join two monomer with the here cross-linker, and then start the oxidation reaction. I mean the oxidation synthesis, and make this a substrate. And here sample get freeze dry and characterize this sample, and then characterize this film making, characterize this XRD, and then XPS, then electrochemical property. We measure here. Finally, we measure the all this here electrochemical analysis, capacitance, retention power, and we have compared our work with the published report. We found here the farad, specific conductance of this system, 480 farad per gram. The reason behind that, the surface area drastically increased. Surface area is too much increased. Even the closed plate hexagonal structure, but surface area too much increased. And as a result of that, we say we observe very high specific conductance. And this work is really fascinating. We can, in a simple 1 method process, we can generate the sub-nanometer ordering in a polymer system, which can improve the functionality of the polymer, and we can select as per the requirement. Either we apply for electronics, photonics, magnetism, or any other artificial intelligence applications. We can select as per our requirement, either the polymer system or monomer or cross-linker. And all this work published, we can see the detail in this reference here, Advanced Material, SCS Applied, Nanoscale, and Polymer, and one more paper in Nature Communication. That's my end of my presentation. I'm open for any question.
Thank you, Dr. Mohammad Shanghez, for your presentation. Is anyone having any questions? Okay, I think there are no questions from anyone. Thank you once again for your presentation.
Sure.
Yeah. As per our list, I would request Dr. Ricardo Acosta to give his presentation now. Hello, Dr. Ricardo.
Hello.
Yeah, are you ready with your presentation?
Let me see. I have never used this
Yeah,
software.
I can explain you. Like, if you are willing to give your presentation now, I can make you the presenter.
Right.
As we are ahead of the time, because two of our speakers had requested that they will join us tomorrow, so we are running ahead of time. So I have make you the presenter. So you're not going to, you have the 4 buttons on your bottom of your screen. That is mic, camera, screen, and leave. Yes. Now it's visible. Your screen is visible to all of us. You can start your presentation. Yes. Yes. Perfect.
You can see my presentation?
Yes.
Right. All right. My name is Ricardo Acosta Ortiz, and I work for the Research Center for Applied Chemistry, which is located in Saltillo, Mexico. The title of my talk is Synthesis of Bio-based Cycloaliphatic Epoxy Monomers derived from nopal. And the study of their cationic photopolymerization. Sorry, it does not go to the next slide. Right. I want to start by mentioning what about epoxy resins. The thermoset polymers derived from epoxy resins are considered as high-performance materials, and this is because of their excellent mechanical properties, high thermal and chemical resistance, low shrinkage during photopolymerization, excellent acidity to substrates. These epoxy resins are very important in the industry, and we can see that because of the global sales of these epoxy resins were of $5,000 million in 2019, with an annual growth of 4%. There are different types of epoxy resins, for instance, glycidyl ethyls, glycidyl esters, glycidyl amines, cycloaliphatic epoxy resins, aliphatic glycidyl resins, and novolog epoxy resins. All these epoxy resins have found multiple applications, for instance, as coatings for different substrates like metals, plastics, paper, etc. Epoxy resins have also been used to prepare composite materials that have found a very wide application in the aerospace and nautic industry, and also as adhesives to prepare pipelines, turbines, in 3D printing, and to prepare electronic circuits. It does not go to the next slide. Oh my gosh. Right. Epoxy resins need to be cured in order to obtain these excellent mechanical properties. There are different types of curing agents, for instance, aromatic diamines, which the amino group can attack the epoxy group to obtain very cross-linked polyamino hydroxy polymer. Another type of curing agents are the tiles, multifunctional tiles, which in the presence of a base could be attacked the epoxy groups and to induce their anionic ring opener polymerization to finally obtain a cross-linked polyether. Another type of curing agents are the catalyst, either basic or acid. We can have, for instance, here the tertiary amines that could be used as catalyst, that the unshared pair of amino group, tertiary amino group, can attack the epoxy groups to induce their anionic ring opener polymerization to produce a polyether. And in the case of the acids, they can protonate or activate the oxygen of the epoxide group to a further attack of a new molecule of epoxy monomer to induce their cationic polymerization to produce a polyether. So in all these cases, a highly cross-linked three-dimensional network of polyethers is produced, which is the responsible of their excellent mechanical properties. However, the epoxy resins have some problems. For instance, the diglacial ethers represents 90% of all used epoxy resins. And of this, the diglacial ether of bisphenol A is the more important resin due to its low cost and high performance. And it is obtained by the reaction between bisphenol A and epichlorohydrin. Here's the chemical structure of this diglacial ether bisphenol A. However, it has been found that bisphenol A has certain toxicity problems. For instance, this bisphenol A can induce teratogenic effects in humans. So this is the reason because the bisphenol A has been banned in several countries, for instance, in Europe and in Canada. So because of this, there is an urgent need to found substitutes for this diglacial ether bisphenol A. And one of these alternatives is to use bio-based epoxy resins. Several renewable sources has been used as a starting material. For instance, rosin, cardinol, isosorbide, lignin, and gallic acid can be subjected to chemical modification, for instance, by epoxidation or by glycidylation to obtain the epoxy monomers that can be further cured to obtain polyethers. In our case, we decided to prepare cycloaliphatic epoxy resins, and we focus our attention in the terpenoid nopal. Here is the chemical structure of nopal. In this, in the cycloaliphatic epoxy cycloaliphatic ring, we can see that we have a double bond that can be used to introduce the epoxy group. And we also have an hydroxyl group that can be used to modify chemically these compounds to prepare the epoxy resins. This nopal is a cheap starting material that comes from the beta-pinene, which is the main component of trementin. So consider this, we prepare three novel nopal epoxy monomers, two trifunctional monomers and one bifunctional. In the monomer N1, we have an acetal monomer with three cycloaliphatic epoxy rings. In the case of the trifunctional monomer N2, we have it has an aromatic tresine ring that is bonded with three nopal moieties. And in the case of the bifunctional monomer N3, we alkylated the nopal monomer with epichlorohydrin to obtain a combination of one cycloaliphatic epoxy ring with a glycidyl ether. We synthesized the monomer N1 by means of an acetalization reaction between 3-cyclohexane, 1-carboxyhaldehyde, aldehyde with two equivalents of nopal in the presence of paratoluene sulfonic acid as catalyst, refluxing in toluene. We obtained this unsaturated intermediate that was further epoxidized by using oxone in acetone as oxidizing agent to obtain the trifunctional epoxy monomer at 75% yield. We characterize this monomer by means of FTIR spectroscopy and proton NMR spectroscopy. In the FTIR spectroscopy, we can see in the first panel the FTIR spectrum of nopal, where we can see a wide band at characteristic of hydroxyl group centered at 3,342 centimeters at -1. We can see the CH band, also a small peak corresponding to the double bonds at 1,646 centimeters at -1. And also we have the CO band at 1,048 centimeters at -1. After the acetalization reaction, we can see the characteristic peak of double bonds here and here, and the appearance of new CO bands at 1,135, 1,097, and 1,071 centimeters at -1. That after epoxidation, we can see the disappearance of the double bonds, the bands of characteristic of the double bonds, and the appearance of new bands at 855 and 779 centimeters at -1. So in the proton NMR spectroscopy, we can see in first place the spectrum of nopal, where we can see a signal at 5 part per million, characteristic of the double bonds. Another peak at 3.6 part per million of the protons adjacent to the hydroxyl group. And also we can see here the signals of all cycloaliphatic protons. In this case, we can see the signals corresponding to the gem dimethyl groups F and G, and D corresponds to the protons of the carbon bridge. After the acetalization reaction, we can see the appearance of new peaks corresponding to double bonds here. And in F, we can see the proton of the acetal group. In G, we can see that these protons correspond to the methylene of the carbon adjacent to the oxygen, and all the methyl and the cycloaliphatic protons. After epoxidation, we can see the disappearance of the double bonds here. We don't have it anymore. And the appearance of new band corresponding to the proton of the epoxide ring of the epoxide groups, and the shifting of the cycloaliphatic protons to lower field because of the saturation of the cycloaliphatic ring. In the case of monomer N2, we prepared this monomer by aromatic substitution, nucleophilic substitution aromatic of the alkoxide of nopal by displacing the chlorine atom in cyanuric chloride in the presence of sodium hydroxide and a phase transfer catalyst as tetrabutyl ammonium bromide to obtain this cycloaliphatic trifunctional monomer with a triazine aromatic core, which was further epoxidized with oxone in acetone to obtain the trifunctional monomer at 70% yield. In the FTIR characterization, we can see that after the aromatic substitution reaction, the appearance of new band at 1,565 centimeters at -1 that correspond to the CN bond. And also there is the displacement of the CO band from 1,050 centimeters at -1 to 1,138 centimeters at -1 because of the bonding of to the aromatic nucleus in the monomer. After epoxidation, we can see the disappearance of the double bonds and the appearance of new bands at 916 and 861 centimeters at -1, corresponding to the new epoxy groups. And in the proton NMR spectrum, we can see that after the the first reaction, the displacement of these protons adjacent to the hydroxyl group to higher field because of the connection to the triazine ring. And after epoxidation, we can see the disappearance of the double bonds and the appearance of a new signal at 3.3 part per million corresponding to this proton in the epoxide group. And in the carbon-13 NMR spectroscopy, we can see that we only have one signal in the aromatic region, which gives us an idea that we only have the trifunctional monomer. If we would have, for instance, the monofunctional or bifunctional monomer, we should have another signal. So this confirms that we have the trifunctional monomer. In the case of monomer entry, we prepared by means of an alkylation reaction of nopal with epichlorohydrin in the presence of sodium hydroxide and the phase transfer catalyst to obtain this unsaturated intermediate that was oxidized to obtain the bifunctional monomer with one cycloaliphatic epoxy group and one glycidyl epoxy group, and it was obtained at 90% yield. In the FDIR spectrum, we can see that after the alkylation reaction, two new bonds corresponding to the epoxy group appeared at 912 and 846 centimeters at -1, and the shifting of the CO bond from 1050 to 1108 centimeters at -1. And after the epoxidation of the intermediate I entry, we can see the appearance of two new bonds at 867 and 858 centimeters at -1, corresponding to the new epoxy group produced in the cycloaliphatic ring. In the proton NMR spectroscopy, we can see the appearance of these three signals corresponding to the epoxide group introduced by the alkylation with epichlorohydrin. And after the epoxidation, we can see the disappearance of the double bond and the appearance of new band here corresponding to this proton joined to the epoxy group. In the carbon-13 NMR spectrum, we can see that there were all the signals corresponding to the desired compound. So this confirms that we have the desired compound. After having synthesized the three monomers, we proceeded to photopolymerize it cationically by using a cationic photoinitiator like the deryl iodonium salt, which is the disiloxyphenyl iodonium hexafluoroantimonate, which are going to call the DPPI. And this cationic photoinitiator was added to the nopal monomers at 1 mol%. And here we have the mechanism of cationic photopolymerization, where we can see that once that the photochemical formulation are irradiated with ultraviolet light, it goes to an excited state from which certain cationic species are produced, for instance, a radical cation and an anion ion, which in the presence of solvent or monomer is produced as superacid. This superacid protonate the epoxide group to obtain this activated species, which can be attacked by a new molecule of epoxide group to produce a polyether. We polymerize the nopal monomers in a UV chamber provided with a fusion UV lamp of 300 watts, and we added the photoinitiator at 1 mol% concentration using a UV light intensity of 40 milliwatts per square centimeter and a resident times of 10 minutes. In order to compare the reactivity of our monomers, we decided to use the real-time FTIR spectroscopy, the RT-FTIR technique that is quite used in photopolymerization. And what we did was to add 200 milligrams of each nopal monomer separately, and then we add the 1 mol% of the photoinitiator, and we cut 2 pieces of polypropylene corona treated film, and then we made a sandwich and we added a drop of the photochemical formulation in between, and we put this sandwich in the sample holder, and the sample holder was put in the sample compartment of the FTIR spectrometer. This spectrometer should have the capability of run successive scans in a determined time. So then we set the UV intensity of 40 milliwatts per square centimeter, and then we started the scanning of the sample. At the same time, we irradiated the sample with the UV light, and we can see that there were a decay in the absorbance of the epoxide groups until the final conversion. From these experiments, we obtained these graphs of conversion of epoxy group versus irradiation time, where we can see that all three monomers display high reactivity, achieving around 50% conversion in the first minute. And then the conversion for monomer N1 was around 53%, and the monomer N2 achieved a conversion of around 56%. And in the case of monomer N3, the conversion was 60%. This high reactivity of these monomers was produced by the higher strain of the cycloaliphatic epoxy group in the monomers. So then we proceeded to determine the glass transition temperature of the polymers derived from the monomers N1, N2, N3. And then we can see that in the case of the polymer derived from monomer N3, the glass transition temperature was 12 degrees, while in the case of both functional monomers, the TGs was 64 degrees Celsius and 66 degrees Celsius, which is coincidentally very similar and could be due to the trifunctionality of the monomers. We also determined the thermal stability of the polymers derived from the noble monomers. And we can see that in the case of the monomer N2, which has the triazine aromatic core, it has the highest thermal stability, followed by the acetal monomer. And the case of these two trifunctional monomer has an onset of around 300 degrees Celsius. And in the case of the polymer derived from the bifunctional monomer, it has a thermal degradation onset of 240 degrees Celsius. So conclusion of this work were that 3 novel epoxy monomers derived from noble were prepared and characterized. The prepared monomer displayed a high reactivity toward cationic photopolymerization. The TG of monomer N3 was 12 degrees Celsius, while monomers N1 and N2 had a TG of 66 and 64 respectively. Trifunctional monomers displayed good thermal stability with an onset of more than 300 degrees Celsius, while bifunctional monomer had an onset of 240 degrees Celsius. So I want to thank the Mexican National Council of Science and Technology, CONACYT, for funding this project. Thanks for your attention, and I will be happy to answer any question.
Thank you, Dr. Ricardo. It was a nice presentation. Is anyone having any questions? Yeah, I think there are no questions. Thank you once again, Dr. Ricardo.
Okay, thank you.
Yeah. So moving on to the next presentation, it is again from Dr. Asia Janaki from Abu Bakr Abdelkad University, Algeria. Hello, Dr. Asia Janaki.
Hello.
Are you ready with your presentation?
Yes.
Yes. I'm going to make you the presenter. Yeah, it's done. Now you can share your screen and start your presentation. Yes, now it's visible.
It's okay?
Yes, yes.
Hello again. I'm Zanaki Asia, PhD student from the University of Tlemcen in Algeria. In this study, we will see the mechanical and thermal properties of annealing film of polyacid lactate. In the past, durable basic materials like stone or iron have played an important role in scarcity. In order to meet the growing need for some of these materials and at the same time improve their precious properties, science and industry of the 20th century develop a new project, which is plastic. They no longer come from agriculture, but petroleum, and the result from spectacular progress in chemistry. Plastics have many properties. They are sometimes incomparable and have favorably replaced many natural products. In variation application, banning plastic would mean that humanity must return to early 20th century life. In order to avoid an environment catastrophe, a change must be done urgently, and among the solution is to switch from plastic from hydrocarbon to bioplastic. The bioplastic help to improve the environment's impact of products in two ways. The use of renewable resources for the manufacture monomer allowed a reduction of in the use of the fossil resource and greenhouse gas emission. As we know, the PLA is a biodegradable plastic. It's used in a lot of applications because of its excellent biocompatibility. However, its degradability and the heat resistance are greatly dependent on its crystallinity structure. The aim of our study is to understand the fundamental effects of annealing on mechanical and thermal properties. The PLA used in this study is supplied by Naturwork. It's semi-crystalline polymer. It's the 4043D grade. To prepare our sample, the previously dried pellets are placed in a vacuum oven at the temperature of 200 degrees Celsius for 30 minutes between two silicone sheets. The film are pressed between two metal plates for 5 minutes, then quenched for 1 minute at 4 degrees Celsius. The films are placed between two plates and left under vacuum at 80 degrees Celsius for different time. And the method used for the analysis is the DSC MQ2000TA equipped with the refrigerated cooling system RCS19 and the DMA Q800. To obtain the DSC thermogram, a sweep thermal was carried out from a room to melting temperature with a heating rate of 10 degrees Celsius. We can see the difference between the sample annealed at 80 degrees Celsius for 3, 6, 10, 18, and 24 hours. The crystalline peak disappears after 3 hours, and the intensity of melt peak increases with time. Here we have a summary of the value of TG, temperature of melt, and crystallinity. We can observe that the crystallinity increases with time from 2% of an annealed film to 90% of the 24 hours of annealing in 80 degrees Celsius. In the mechanical analysis, tensile clamp is used. We can see the caoutchouc plateau from 6 hours of annealing because the samples are semi-crystalline, and the modulus E decrease with the time. For the value of TG, they remain constant, but the intensity of the peak of the tangent delta change. A weight measurement has been done using a viscosimeter in order to explain the relation between crystallinity and the modulus E. Indeed, when the time of annealing increase, we observe that the crystallinity increase, but the modulus E increase at 3 hours and decrease after this. This can be explained by degradation of polymer after 3 hours. We can see a mass drop because of the low crystallinity of sample. But after this time, the film is crystalline enough to prevent the degradation. The heat treatment have an important impact of the PLA film. The crystallinity increase and in another hand, the rigidity decrease. Sorry, the rigidity decrease with the time because of the degradation and crystallization. We conclude that there is a competition between crystallinity and degradation, and to determine the property of PLA, we have to study more annealing time and find the balance between the two phenomena. And thank you for your attention. If you have any question, I'm here. There is no question? Okay, thank you so much.
Hello, this is Sudhir Bhavna from Tucson, Arizona. I'm on the line and I'm ready to present whenever you want.
Hello, Dr. Asia.
Yes.
Yeah. Is there any problem?
No, I finished. I hope that
Okay.
it was clear.
Yeah. Okay. Thank you. Thank you very much for your presentation. Is anyone having any questions on this presentation?
I hope that it was clear.
Yeah. Okay. Thank you, Dr. Asia, for your once more.
Thank you very much, and thank you for your organization.
Yeah. So moving on to our last presentation of day one webinar, it is from Dr. Sudhir Bhavna from Raytheon Missiles and Defense, that is from USA. Hello, Dr. Sudhir Bhavna. I'm going to make you the presenter.
Yeah, you need to give me permission to present.
Yes, it's done. Yeah, I have given you the permission. Please click on the screen button. Yes, now it's visible. You can start your presentation.
Okay,
Yes.
can you see my?
Yeah, it's visible.
Okay, hang on a minute. Let me. Okay, so can everyone see my slides?
Yes, it's visible.
Okay, so I am going to present a proposed method to determine aging activation energy for elastomers and see how valid it is. So the reason this is important is in industry, hardware may be built today, but may need to function several years later. So there will be aging of organic materials during that time. And we need to be sure that the organic materials such as, and I'm specifically addressing elastomers and rubbers in this presentation, will still perform as intended. For example, you may have an O-ring seal, and we need to be sure that the O-ring rubber will obviously degrade with time, but will it degrade to an extent that becomes unacceptable? So that's the objective. I'll present the background, share the materials and test methods, provide results on a Parker butyl elastomer grade B0612-70, a nitrile, EPDM, polychloroprene, and low temperature fluorocarbon. So a wide range of elastomers, and we'll see what conclusions can be drawn from that data. So the objective, as I said, is there is a Ozawa-Flynn wall method by weight loss by thermogravimetric analysis, or TGA, for determining aging activation energy or determining activation energy of elastomers for ASTM test method E1641. And is that the value so obtained appropriate for using aging studies? And as I mentioned, aging studies and data are essential for life determination and life expectancy. So aging studies are expensive and take a long time. For example, Sandia Laboratories, and the point 1 on the screen, did by Bernstein, published in the journal Polymer Degradation and Stability in 2010. They reported on a nylon 66 aging study at 37 degrees C was the oven aging temperature, and it lasted 2,000 days, which is 5.5 years. So clearly in industry, waiting 5.5 years to reach a conclusion is not an option. So weight loss by TGA for ASTM E1641 is an attractive, since it's a quick and it takes few hours to a couple of days at most as compared to 2,000 days. It's convenient since it's automated equipment and the software does all the calculations and number crunching, and it's inexpensive. So bullet 3. But there are several caveats. Bullet 3, for example, paragraph 5.2 of ASTM E1641 says, this test method can be used for estimating lifetimes of materials using ASTM E1877, provided that a relationship has been established between the thermal endurance test results, which are at very high temperatures, and actual lifetime tests. And most of the time, such correlations are never available. And paragraph 5.6 of ASTM test method E1641 says, this practice shall not be used for product lifetime predictions unless a correlation between test results and actual lifetime has been demonstrated. And again, such correlations are almost never available. So there are already some flags being raised by the ASTM test method itself as to the applicability of the method for determining aging activation energy to be used at room temperature aging for many years or decades. And bullet 5.6 of ASTM E1641 says, in many cases, multiple mechanisms occur during the decomposition of a material, which is what TGA thermogravimetric analysis does, with one mechanism domination over one temperature range and a different mechanism dominating in a different temperature range. Users of this practice are cautioned to demonstrate for their system that why temperature extrapolations are technically sound. So we need to make sure that the oven aging temperature, so the higher the oven aging temperature, the shorter the aging time. But so that's attractive in getting data quickly. But the oven aging temperature cannot be so high that it changes the degradation mechanism from the mechanism that is prevalent for room temperature aging over several years or several decades. So the takeaway is there is no fundamental reason why activation energy for ASTM E1641 should be the same as activation energy for room temperature aging, though if that were true, that would be very helpful and attractive. Here are the materials and test methods. So I already went over the elastomers. The TGA testing was done using a TA instruments test and its weight loss. The heating rates used were 1, 2, 4, 6, and 8, and 10 degrees centigrade per minute, conforming to paragraph 10.5 of ASTM E1641. And I will also be showing some compression set testing, which was done for ASTM D395 method B. So there are 5 different elastomer studies, so that spans a significant range. So for the Parker butyl B612, there is published data that the activation energy using compressive stress relaxation is somewhere in the range of 78 to 80 kilojoules per mole, and by oxygen consumption, it's 78 to 82. So everything is around 80 kilojoules per mole. And the Parker butyl B612 formulation is a commercial Parker formulation. It is proprietary. And below is the reference from Polymer Degradation and Stability 2003 article by Gillen, from which I got these numbers. And we will compare these activation energy values versus the activation energy values, which I will show you I obtained from TGA for ASTM E1641. So here is the nitrile formulation that was studied, and we will be using literature data for reference number 17 from Polymer Degradation and Stability journal published in 2001. And you can see the sample that I prepared to do TGA is virtually same. So HICAR 1052 and NIPOL 1052 are the same since 2001. The trade name for HICAR has changed to NIPOL, but that doesn't mean the chemical composition of the material has changed. And the only other change is MBTS, the material. I listed the grade. So it is the same formulation. Here is similarly the EPDM formulation. So Nordel 1440 is no longer available, so it was replaced by the closest equivalent, which is Nordel 4640. And you can see from the ethylene, etc., compositions, both are terpolymers. So it's a reasonable and close replacement. The N539 carbon black is no longer available. The closest one is N550. The zinc oxide is the same. And the Flectol H antioxidant is replaced by azurite resin D antioxidant, and they are the same chemical material. The polychloroprene formulation is shown here, and we use exactly what is in the published literature. And the polychloroprene activation energy from other techniques on the leftmost column are for non-Clayfield formulation, which is what is reported. And you can see there is a wide range depending on which test method or which parameter is used to monitor it, whether it's oxygen consumption, and it's below ATC for the reason mentioned, that we don't want to go so high in temperature that the degradation mechanism changes, whether it's modulus, it's FTIR signal, it's carbon dioxide or carbon monoxide production. And commercial polychloroprene formulations have a filler such as clay, and you can see those numbers don't have as much of a spread. Moving on to fluorocarbon. So the fluorocarbon literature data is not available for the specific formulation we use. And so here is compression set data ranging from 6 hours to 8760 hours, so a year, and that's a really long time. And the temperatures range from 70 C to 300 C. So that's a lot of data encompassing a very wide range. And on this screen is the data is plotted. So it's exactly the same data as a previous slide, except now it is in a graphical form with compression set on the y-axis and the compression time on the x-axis. Then here is the data after shifting it to a reference temperature of 125 degrees centigrade. And you can see there are multiple degradation mechanisms, which again drives home the point that if you go to a higher temperature, the degradation mechanism will change. So at very low temperatures, near room temperature, the activation energy is extremely small, only about 6 kilojoules per mole. At higher, it's 50 kilojoules per mole. and the shift factors 80 are listed in the graph. The x-axis is the compression set. The x-axis is time on a logarithmic scale, log 10 hours, and on the y-axis is compression set. So now we will look at the activation energy by TGA. And for weight loss varying from 1% to 10%, you can see that different values for different materials are listed. And you can see generally they show a trend of increasing as weight loss increases. The average and median values are listed. So the conclusion is, and also if you look at the second and third column, it's butyl B612 in air and nitrogen, and air will give higher values. The test method requires in nitrogen, so all the others are in nitrogen only, but this is to drive home the point that presence of oxygen will speed up the degradation as one would expect. So this is the most important slide for the presentation. Here is the final conclusion. So on the first column from the left, the elastomer type is listed. On the second column is 1% weight loss or activation energy corresponding to 1% weight loss, then 5% weight loss, then 10% weight loss, then the average of 1 to 10, and then the median of 1 to 10. And the rightmost column gives the activation energy by other techniques. So if we look at activation energy of butyl B612, at 1% weight loss, it's already 93, and that decreases and increases as the weight percent increases, but that's higher than the literature reported oxygen consumption activation energy of 78 or around 80. The nitrile shows the opposite trend very strangely, and I don't quite understand why it's showing an opposite trend, because we looked at the formulations. So it's 56 at 1% and then increases, but it's 80 by oxygen consumption below 65 degrees centigrade reported in literature. EPDM again shows high values, 114 at 1% versus 82 measured by monitoring elongation, density, oxygen consumption below 111 C reported in literature. Then the non-clay filled polychloroprene is 66 at 1% and increases at weight percent increases, but it's only 37 as reported in literature for oxygen consumption below 82 degrees C. And lastly, the low temperature fluorocarbon, for which there was no literature data, it's 164 by 1% weight loss, but only 6 kilojoules per mole, with a compression set in the 70 to 175 degrees C range. So from this data, we can conclude that the activation energy using thermogravimetric analysis, while very attractive because it's a quick, cheap, easy test to do using Ozawa-Flynn-Wall method per ASTM E1641, does not agree with other techniques and generally vastly overestimates the activation energy, which will lead to erroneously high lifetime predictions. So this work has been published in the Journal of Elastomers and Plastics online on 31st May of this year. And there is a link there that you can click and link and buy for $42, or you can email me and I can mail you a free copy. So that's it. Now I will take questions. So you can either verbally ask the questions or you can type it in the chat room and I will read them out and answer your questions.
Thank you, Dr. Sudhir. Hello, Dr. Sudhir. This is a very nice presentation. Is anyone having any questions? Thank you once again. I think there are no questions. So our next day presenter, that is Dr. Elham Ben Khalifa, requested us that he will be presenting today as he will be not available tomorrow. So we will make the present to Dr. Elham Ben Khalifa. Hello, Dr. Elham. Are you ready to give the presentation?
Hello. Yeah, I'm ready.
Yeah. Okay. So I'm going to make you the presenter. Yeah, it's done. Now please click on the screen button, share your screen and start your presentation.
So I will share with you my screen.
Yeah.
It's clear?
No, it's not visible. Did you click on the button screen?
Okay, just 1 minute.
Okay.
And now?
Yes, it's now visible. You can start your presentation.
Okay, thank you. So good afternoon, everyone. This is Ben Khalifa Ahlam. I'm PhD student in University of Tlemcen, Algeria. First, I would like to thank the organizers of this interesting conference. Thank you very much for this amazing opportunity and your hard work. However, my presentation titled is Swelling Kinetic of Novel Sequential Interpinated Polymer Network composed of 2-ethyl hexyl acrylate and isobonyl acrylate. So, sorry. Just 1 minute.
Dr. Elham?
My presentation is divided into 5 parts.
Okay.
I will start by introduction. Then I will look at literature review, material and methods, experiments and results, and finally I will finish by conclusion. In last years, many researchers have studied this science of polymer gels. This is due to the potential industrial application of this kind of polymer system. The attention was to focus on the innovation and development of new materials for these systems. The major shortcoming of this kind of polymer network is their poor mechanical properties when they are in the swelling rate. So the increasing in the cross-link density and copolymerization with a more resistant system are among the way to reinforce this system, as well as the formation of interpinated polymer network IPNs. So what is an IPN? An interpinated polymer network, or IPN, known as a blend of at least 2 polymers in a network form when them is entities or and crosslink in immediate presence of the others. The entities of this new material class make it possible to have in certain case new materials with a good performance in comparison with the initial polymer precursor. These polymer networks are synthesis by any known method of polymer synthesis. The most used approach for the synthesis of IPNs or interpinated polymer network are the first polymer network is synthesis, then the second monomer plus crosslinker plus activator are swollen into network 1 and polymerized in situ. The resulting IPN is called sequential IPN. In the second case, the monomers or homopolymers plus crosslinker and activator of both components are mixed, followed by simultaneous polymerization. Typical synthesis in body chain and step polymerization kinetics. Well, both polymerization proceeds, the reaction ratio are rarely identical. So in order to use interpenetrating polymer network for practical application, it is required to understand the difference between the properties of these polymer networks. In this work, a novel sequential IPN based on ethyl hexyl acrylates, EHA, and isobornyl acrylic as hard polymers. View of their complementary properties, blending polyisobornyl acrylates and ethyl hexyl acrylates is a natural choice to improve properties, including rigidity. Two kinds of sequential IPN, were syntheses. The first one consists of polyisobornyl acrylate networks swollen until reaching equilibrium in a solution containing the second monomer, AHA plus crosslinker plus photoinitiator. The swollen sample was then exposed to UV irradiation. Generally, the exposure time was fixed at 30 minutes to achieve a complete conversion of all monomers in the precursor system. The resulting network will be called IPN1. The second IPN was obtained with the same methods described above, except that the first poly-EHA network was formed, which was swollen in a second step, until reaching equilibrium by a solution containing isobornyl acrylates. For tear analysis, changes of absorbance of the band at 810 were considered to present the evolution of photopolymerization reaction during UV irradiation. Also show that an irradiation time of 35 minutes make it possible to obtain a maximum conversion of the acrylic function around 98%. Swillen ratio. This figure constitutes a measure of the quantity of reactive solution absorbed by the two different polymer networks. As the time proceeds, the two reactive solutions diffuse in the network due to the concentration gradient resulting in the exponential swelling of the network. From the same swelling curve, it is observed that the two polymer networks have a practically similar physical behavior. That is to say, they swell both in the same way and in the same speed. We can also say that the two polymer networks have a maximum swelling ratio around 475 for poly-EHA network and 288 for polyisobornyl acrylates, which means that each network can swell up to 3 times its initial volume. With a small logic, each network contains the equivalent of 3.5 network in addition to initial networks. For the thermal analysis, was carried out to know the phase separation behavior that can exist in the different polymer network. The study focusing in the second heating, that is to say, the first cycle of temperature variation -70 to 120. Having obtained a similar curve for the 3 tests, we present only one curve for each composition. This figure represents the glass transition temperature variation of the different networks. Only one single transition in DSC curves for all the network is detected, especially only one single transition in the DSC curves for all the polymer is detected, especially for the two synthesis IPNs, which indicates that the IPNs don't present phase separation. This would suggest that the different monomers, AHA and isobornyl acrylates, are perfectly miscible. In addition, this figure informs us that the glass transition temperature of both IPNs are close to each other and are controlled first by the quantity of precursor polymer network present in the mixture. And the glass transition temperature of IPN1 show a slight shift compared with the TG of poly-EHA network. Apparently with the presence of polyisobornyl acrylate in the IPN1. This decrease in glass transition temperature was accepted because in the network IPN1, where the presence of monomer EHA is governing. This law tends to influence in behavior and those who have glass transition temperature more or less close to that the pure network poly-EHA and isobornyl acrylate. So in conclusion, in this work, we demonstrate the synthesis of novel sequential antikinetic polymer network composed of polyhexyl acrylate and isobornyl acrylate. The system swell exponentially to saturation over 48 hours due to the concentration gradient. The DSC results inform us that the glass transition temperature of the different studied system is influenced by the amount of the monomers absorbed by the network, and that all the result IPNs, especially the IPN with the 0.5% cross-link does not present any phase separation. Thank you for your attention.
Thank you, Ms. Elham Ben Khalifa, for your presentation. Is anyone having any questions? Okay, I think there are no questions. Thank you once again. So by this, we came to end of our day 1 webinar. I would like to thank all the attendees and participants of today's webinar. Hope you enjoyed the webinar and gained knowledge from the sessions, and request you to attend tomorrow's sessions also. If you have any queries, you can mail us to the concerned program manager.
Thank you very much.